Welcome to Scientific Discovery Hub, where we explore the universe's most mind-bending mysteries. Today we are diving into a cosmic detective story, the interstellar comet 3I Atlas, and how its journey through our solar system unveiled secrets about the Milky Way's ancient past. Buckle up, we're about to travel billions of years back in time. In 2025, astronomers spotted something extraordinary, a comet speeding through our solar system at over 58 kilometers per second, its path unmistakably interstellar. Named 3I Atlas, this icy wanderer became only the third confirmed visitor from another star system. But this wasn't just a passing spectacle. Its hyperbolic trajectory, ancient origins, and strange chemistry hinted at a deeper truth, one tied to the Milky Way's hidden architecture. How could a tiny comet rewrite our understanding of the galaxy's history? Let's break it down. First, we'll follow 3I Atlas's dramatic journey, from its discovery by NASA's Atlas survey to its slingshot past the Sun and Mars. Then, we'll explore the Milky Way's layered cake structure, the thin disk where our Sun lives, and the thick disk, a fossilized remnant of the galaxy's violent youth. Using cutting-edge tools like the Hubble and James Webb Space Telescopes, scientists linked 3I Atlas to the thick disk, a region so old it predates the solar system itself. Could this comet be a 7-billion-year-old relic from a forgotten era of star formation? We'll also uncover the alien chemistry of 3I Atlas's Coma, rich in carbon dioxide and organic compounds, and tackle the challenges of studying such a faint, distant object. Along the way, we'll address the buzzworthy controversy. Could it be an alien spacecraft? Spoiler: science has answers, but the debate highlights how interstellar objects push the boundaries of our knowledge. Finally, we'll peer into the future, imagining missions that might one day intercept these cosmic messengers and ponder the profound idea that comets like 3I Atlas could bridge star systems, spreading the building blocks of life across the galaxy. So, if you've ever wondered how a single comet could expose the Milky Way's deepest secrets, or just love stories of cosmic adventure, you're in the right place. Hit play to join us on this journey through time, space, and the science that connects them all. And don't forget to subscribe for more explorations into the wonders of the universe. In the vast, silent expanse of the cosmos, where stars burn like distant lanterns and galaxies swirl in elegant spirals, a lone traveler arrived in 2025 to whisper secrets of the universe's ancient past. 3I Atlas, the third confirmed interstellar object to traverse our solar system, is more than a fleeting visitor. It is a relic of a time when the Milky Way was young, a time when stars and planets were born in the crucible of stellar nurseries. Its arrival, marked by a hyperbolic trajectory and a velocity exceeding 58 kilometers per second, defies the familiar rhythms of our celestial neighborhood. This comet, with its icy heart and dusty coma, is a cosmic messenger, carrying fragments of a story that predates the solar system itself. What mysteries does it hold, and how does its journey reshape our understanding of the galaxy's hidden architecture? 3I Atlas was discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, in Chile, a network designed to detect objects that might threaten Earth. Yet, this discovery proved far more profound. At the time of its identification, the comet was hurtling through the inner solar system at a distance of 4.5 astronomical units, AU, from the Sun, its path already betraying its interstellar origin. Unlike asteroids, which are rocky remnants from planetary formation, comets like 3I Atlas are icy bodies that preserve the primordial materials of their birthplace. The Sun's heat sublimates these ices, releasing gas and dust to form a glowing coma, and sometimes a tail. But 3I Atlas's behavior is distinct. Its coma is unusually rich in carbon dioxide, a signature that suggests it formed in a region far colder than the water ice line of its home system. The comet's trajectory is a testament to its interstellar heritage. With an orbital eccentricity of 6.14, its path is nearly straight, a hyperbola rather than an ellipse, indicating that it is unbound by the Sun's gravity. This extreme trajectory means 3I Atlas will escape the solar system entirely, after its closest approach to the Sun on 29 October 2025. Its velocity, a blistering 68 kilometers per second at perihelion, surpasses that of its predecessors, One-Eye Oumuamua and Twin-Eye Borisov, by nearly double. Such speed implies that Three-Eye Atlas has not been perturbed by the gravitational influence of any solar system planet, a fact that confirms its extragalactic origin. Yet, its path is not random. The comet's trajectory aligns closely with the ecliptic plane, the flattened disk where the planets orbit, suggesting a complex history of gravitational interactions in its native star system. Observations by the Hubble Space Telescope and the James Webb Space Telescope have unveiled the comet's enigmatic nature. Its nucleus, though shrouded in a coma spanning tens of thousands of kilometers, is estimated to be no larger than a kilometer in diameter. Despite its diminutive size, Three-Eye Atlas emits copious amounts of carbon dioxide, water vapor, and cyanide gas, substances rarely seen in such quantities in solar system comets. These emissions paint a picture of a body that has preserved volatile compounds since its formation, untouched by the thermal processing that reshapes comets in our own system. The presence of atomic nickel vapor, a substance typically associated with cometary activity, further underscores the comet's dynamic chemistry. The discovery of Three-Eye Atlas challenges long-held assumptions about the rarity of interstellar objects. For decades, astronomers theorized that such visitors would be exceedingly rare, their chances of crossing paths with the solar system infinitesimal. Yet, the confirmation of 3 interstellar objects in just 7 years, Oumuamua, Borisov, and now Three-Eye Atlas, suggests that the galaxy is a far more interconnected place than previously imagined. These travelers are not mere anomalies. They are evidence of a cosmic exchange, a continuous flux of material between star systems. Each one carries a piece of its origin, offering a window into the conditions of distant stellar nurseries. Moreover, Three-Eye Atlas's age, estimated at 7 to 14 billion years, raises profound questions about the timeline of the Milky Way. If the comet indeed hails from the galaxy's thick disk, a population of ancient stars that predates the younger thin disk where our solar system resides, it could have formed in an era when the Milky Way was still coalescing. This would mean that Three-Eye Atlas is not only older than the solar system 4.6 billion years, but also a witness to the galaxy's violent youth, when collisions between young stars and protoplanetary disks were commonplace. Its survival through such chaos is remarkable, a testament to the resilience of these interstellar wanderers. The comet's composition also offers clues about the diversity of planetary systems. The abundance of carbon dioxide in its coma suggests that it formed in a region far from its parent star, where temperatures were frigid enough for CO2 to condense into ice. This parallels the formation of comets in our own outer solar system, such as those in the Oort cloud. But with a critical difference, Three-Eye Atlas's origin is tied to a foreign star system. By studying its chemistry, scientists hope to reconstruct the conditions under which it formed, shedding light on the universality or uniqueness of planetary formation processes. Perhaps most intriguing is the possibility that Three-Eye Atlas could serve as a Rosetta Stone for interstellar comets. Its trajectory and composition provide a template against which future discoveries can be compared, helping to distinguish between comets from different galactic populations. For instance, the high orbital inclination of Three-Eye Atlas tilted 175 Drach relative to the ecliptic suggests that it may have been ejected from a binary star system, where gravitational interactions between 2 stars could have hurled it into the void. Such insights could refine models of how interstellar objects are born and dispersed, ultimately deepening our understanding of the galaxy's dynamic history. Yet, the story of Three-Eye Atlas is incomplete without knowing where in the Milky Way it originated. The galaxy is a layered tapestry, with the thin disk hosting young stars like our Sun, and the thick disk cradling ancient metal-poor stars. Could Three-Eye Atlas's trajectory and composition be traced back to one of these populations? To unravel this mystery, we must delve into the galactic anatomy of the Milky Way, exploring how the thick disk's unique properties might explain the comet's ancient age and its improbable journey to our corner of the cosmos. To understand where Three-Eye Atlas came from, we must peer into the heart of the Milky Way's history. The galaxy is not a uniform expanse, but a stratified structure, with the thin and thick disks representing two distinct epochs of star formation. The thick disk, a relic of the galaxy's violent youth, is home to stars older than 10 billion years, many of which formed in chaotic mergers and collisions. If 3I Atlas indeed originated from this ancient layer, its journey becomes a bridge between the past and present, a fragment of the Milky Way's earliest days. What can the thick disk teach us about the comet's origins and about the galaxy itself? The Milky Way's thick disk is a sprawling, warped structure that extends above and below the galactic plane, housing stars with lower metallicities, abundances of elements heavier than helium compared to those in the thin disk. These stars are among the oldest in the galaxy, their light a fossil record of the early universe. The thick disk likely formed during a period of intense star formation and galactic instability, possibly triggered by mergers with dwarf galaxies. Stars in this region have higher velocities perpendicular to the galactic plane, giving them trajectories that oscillate vertically through the disk. This dynamic environment could have played a role in the ejection of 3I Atlas from its parent system. Tracing 3I Atlas's origin involves analyzing its hyperbolic excess velocity, the speed it carried when it entered the solar system. By decomposing this velocity into components relative to the galactic center, astronomers have determined that the comet approached the solar system from the direction of the galactic center, near the constellation Sagittarius. More importantly, its vertical velocity component, Watts Pons 18.5 kilometers per second, indicates that it is moving upward through the galactic plane, a characteristic shared by thick disk stars. This alignment strongly suggests that 3I Atlas is a member of the thick disk population, placing its origin in a region of the galaxy where stars are ancient and metal deficient. The implications are staggering. If 3I Atlas formed in the thick disk, it could be a remnant of the galaxy's earliest star-forming regions, where molecular clouds collapsed to birth the first generations of stars. These regions were rich in hydrogen and helium, but poor in heavier elements, a condition reflected in the comet's composition. The scarcity of metals in thick disk stars mirrors the low abundances of elements, like carbon and nitrogen in 3I Atlas, reinforcing the hypothesis that it formed in this ancient environment. Furthermore, the comet's high orbital inclination and retrograde motion, its path tilting 175° relative to the ecliptic and moving in the opposite direction to most solar system bodies, may be explained by gravitational interactions in the thick disk, where stars and dark matter exert complex forces. The thick disk's role in 3I Atlas's origin reshapes our understanding of interstellar comets. For years, models predicted that most interstellar objects would hail from the thin disk, where young stars are abundant. However, 3I Atlas's trajectory and age challenge this assumption, suggesting that the thick disk is a significant source of interstellar debris. This realization has profound consequences for the study of galactic evolution. If interstellar comets like 3I Atlas are common products of the thick disk, they could serve as tracers of the galaxy's oldest regions, providing direct samples of material from the Milky Way's formative years. Additionally, the comet's ancient age, potentially exceeding 7 billion years, means it predates the solar system by over 2 billion years. Such an object could contain pristine materials from the early universe, untouched by the processes that reshape the solar system. For example, the high abundance of carbon dioxide in 3I Atlas's Coma suggests it formed in a region where temperatures were low enough for CO2 to freeze, a condition that may have been more prevalent in the early galaxy. By studying these volatile compounds, scientists can infer the thermodynamic conditions of the thick disk at the time of the comet's formation, offering a glimpse into the galaxy's cryogenic past. The thick disk's turbulent history also provides clues about how 3I Atlas escaped its parent system. In this region, gravitational interactions between stars and binary systems could have easily perturbed the comet's orbit, hurling it into interstellar space. Computer simulations suggest that such ejections are more probable in dense stellar environments, where close encounters between stars and planets can destabilize orbits. If 3I Atlas was flung from a binary star system, its trajectory would bear the scars of this chaotic history. explaining its high velocity and retrograde motion. This scenario underscores the dynamic nature of the thick disk, where the gravitational dance of stars and planets shapes the destiny of interstellar travelers. While the thick disk offers a plausible origin for 3I Atlas, its journey through the galaxy is far from complete. The comet's path will take it past Mars and Jupiter, planets whose gravitational fields could subtly alter its trajectory. Yet, these interactions are not the only forces at play. To fully grasp 3I Atlas's fate, we must consider the broader cosmic web, the intricate network of stars, gas, and dark matter that governs the motion of interstellar objects. In the next segment, we will explore how the Milky Way's gravitational field and stellar encounters shape the comet's voyage, guiding it toward its eventual escape from the solar system. As 3I Atlas hurtles through the solar system, it is not alone in its journey. The gravitational pull of planets, the unseen tug of dark matter, and the chaotic interactions with passing stars all conspire to shape its trajectory. Though the comet's path is ultimately destined to escape the sun's grasp, its brief encounter with the inner planets offers a chance to study how interstellar objects interact with our celestial neighborhood. What lessons does 3I Atlas's flight impart about the delicate balance of forces that govern the cosmos? 3I Atlas's closest approach to the Sun, on 29 October 2025, places it between the orbits of Earth and Mars, a region teeming with planetary activity. While the comet will not pose a threat to Earth, its minimum distance of 1.8 AU keeps it safely beyond the Moon's orbit. Its passage by Mars and Jupiter will leave subtle imprints on its path. On 3 October 2025, 3I Atlas will pass 0.19 AU from Mars, a distance close enough for the red planet's gravity to exert a minor influence. Similarly, on 16 March 2026, the comet will sweep past Jupiter at 0.36 AU, an encounter that could alter its trajectory by a fraction of a degree. These interactions, though small, are part of a larger cosmic choreography where the gravitational fields of planets act as invisible hands guiding the comet's flight. The comet's motion is also influenced by the Milky Way's gravitational field, a vast invisible scaffold that shapes the orbits of stars and interstellar objects alike. The vertical component of 3I Atlas's velocity, watts, 18.5 kilometers per second, indicates that it is moving upward through the galactic plane, a motion that will continue as it exits the solar system. This vertical drift, combined with its retrograde motion, suggests that 3I Atlas's path is not confined to the solar system's ecliptic plane, but is instead a product of the galaxy's broader gravitational dynamics. Over millions of years, the comet's trajectory will be further shaped by encounters with other stars and interstellar clouds, each interaction nudging it along a new course. Perhaps most fascinating is the role of stellar encounters in sculpting 3I Atlas's journey. AMPA's study by Yang Guo and colleagues revealed that the comet may have passed within 1 parsec 3.3 light-years of 25 known stars in the past 10 million years. These close encounters, though rare on a human timescale, are frequent enough in the galactic context to significantly alter the comet's orbit. Each star it brushes past acts as a gravitational lens, bending its path in ways that are difficult to predict. Over time, these perturbations accumulate, transforming 3I Atlas from a rogue interstellar object into a participant in the galaxy's endless cycle of motion and change. The gravitational interactions experienced by 3I Atlas offer a microcosm of the forces that govern the universe. Planets, stars, and dark matter all play roles in shaping the comet's path, illustrating the interconnectedness of cosmic scales. For instance, the comet's close approach to Mars, though seemingly insignificant, highlights how planetary gravity can influence the trajectories of interstellar objects. While 3I Atlas will not collide with Mars, the red planet's pull will impart a tiny but measurable change to the comet's velocity, a reminder of the delicate balance that keeps the solar system stable. Similarly, the comet's encounter with Jupiter underscores the gas giant's role as a gravitational gatekeeper. Jupiter's immense mass makes it a dominant force in the solar system, capable of deflecting comets and asteroids into new orbits or expelling them entirely. The fact that 3I Atlas will pass within 0.36 AU of Jupiter raises the question: could this encounter have altered the comet's trajectory in a way that affects its long-term fate? While the change is likely minimal, it serves as a reminder that even the smallest gravitational tugs can have cascading effects over time. On a grander scale, 3I Atlas's journey through the Milky Way's gravitational web illustrates the dynamic nature of interstellar space. The comet's vertical motion through the galactic plane and its retrograde orbit suggest that it is part of a population of interstellar objects with diverse origins and trajectories. This diversity challenges the notion that interstellar comets are rare, instead painting a picture of a galaxy in constant motion, where stars and planets continuously exchange material. Future discoveries of interstellar objects will likely reveal even more about the gravitational forces that bind the Milky Way together, refining our understanding of galactic dynamics. As 3I Atlas prepares to exit the solar system, its legacy as a cosmic wanderer becomes clear. Yet, its story is not merely one of motion and gravity. It is also a tale of observation and discovery. From the ground-based telescopes that first glimpsed its Coma to the space observatories that dissected its chemistry, humanity's tools have played a crucial role in unraveling the comet's mysteries. In the next segment, we will examine how the scientific instruments deployed to study 3I Atlas have expanded our knowledge of interstellar comets, setting the stage for future explorations of the cosmos. The study of 3I Atlas is a testament to humanity's ingenuity and perseverance. From the moment it was spotted by the Atlas Survey in Chile, a global network of telescopes, both ground-based and spacefaring, raced to capture every detail of this interstellar visitor. These instruments, ranging from the Hubble Space Telescope to the James Webb Space Telescope, have transformed 3I Atlas from a distant speck into a vibrant portrait of alien chemistry and ancient history. How have these tools redefined our ability to explore the cosmos? The discovery of 3I Atlas was made possible by the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of telescopes designed to detect near-Earth objects. However, its interstellar nature was confirmed through a collaborative effort involving observatories worldwide. The Zwicky Transient Facility, ZTF, and the Very Large Telescope, VLT, provided critical pre-discovery data, tracing the comet's path back to its entry into the solar system. Meanwhile, the Hubble Space Telescope delivered high-resolution images of the Coma, revealing its structure and constraining the nucleus's size. The James Webb Space Telescope, JWST, with its infrared capabilities, probed the comet's chemistry, detecting carbon dioxide, water ice, and organic molecules. Together, these instruments created a multi-dimensional view of 3I Atlas, a mosaic of light and data that transcends the limits of individual observations. One of the most remarkable achievements in studying 3I Atlas was the use of spectroscopy to analyze its composition. Spectroscopic observations by the VLT and the Swift Observatory identified cyanide gas and atomic nickel vapor in the Coma, substances that are both familiar and alien. The detection of nickel in particular was unexpected, as it is typically found in comets alongside iron. The absence of iron in 3I Atlas's emissions raised questions about the comet's formation environment, suggesting that it may have formed in a region with unique chemical conditions. These findings underscore the power of spectroscopy to decode the secrets of interstellar objects, turning light into a map of their elemental makeup. Another breakthrough came from the SPHERICS mission, which revealed the presence of carbon dioxide gas in 3I Atlas's Coma at unprecedented levels. This discovery challenged existing models of cometary chemistry, which assumed that water dominates outgassing processes. Instead, 3I Atlas's CO₂-Rich emissions hinted at a formation site far from its parent star, where temperatures were low enough for carbon dioxide to condense into ice. By comparing these data with observations of solar system comets, scientists are beginning to draw parallels between the chemistry of interstellar and indigenous comets, suggesting that the processes of planetary formation may be universal. The tools used to study 3I Atlas have not only deepened our understanding of interstellar comets, but have also pushed the boundaries of observational astronomy. The collaboration between ground-based and space-based telescopes exemplifies the power of a global scientific community, where data from disparate sources converge to form a coherent picture. For example, the Hubble's optical imaging and the JWST's infrared spectroscopy complement each other, allowing scientists to study the comet's nucleus, Coma, and tail with unparalleled clarity. Similarly, the involvement of amateur astronomers who contributed observations of 3I Atlas's pre-discovery trajectory highlights the democratization of astronomical discovery in the digital age. Moreover, the study of 3I Atlas has demonstrated the importance of advanced instrumentation in exploring the cosmos. The JWST's ability to detect carbon dioxide and water ice in the comet's Coma is a direct result of its cutting-edge technology, which includes instruments like the near-infrared spectrograph, NIRSpec. These innovations not only enhance our ability to study interstellar objects, but also pave the way for future missions, such as the proposed Interstellar Object Intercept mission, which could one day send a probe to intercept an interstellar visitor. The lessons learned from 3I Atlas will also inform the design of next-generation telescopes and space observatories. For instance, the discovery of the comet's CO₂-rich composition suggests that future instruments should prioritize the detection of volatile compounds, which are key to understanding the formation of planetary systems. Additionally, the study of 3I Atlas's trajectory and age has highlighted the need for better models of galactic dynamics, a field that will benefit from upcoming missions like the European Space Agency's Euclid satellite. As 3I Atlas continues its journey through the solar system, its story remains unfinished. Yet the tools and techniques developed to study it have already laid the groundwork for future discoveries. The next chapter in this cosmic saga will unfold as the comet departs our system, leaving behind a trail of questions and a legacy of scientific advancement. In the final segment, we will reflect on the broader significance of 3I Atlas, not just as a scientific curiosity, but as a symbol of humanity's quest to understand the universe. 3I Atlas's journey through the solar system is a fleeting moment in the grand tapestry of the cosmos. Yet its impact reverberates far beyond its brief apparition. As it departs our system, the comet leaves behind a legacy of discovery, a testament to the power of human curiosity and technological ingenuity. But 3I Atlas is more than a scientific marvel. It is a bridge between worlds, a reminder that the universe is a vast interconnected expanse where the stories of distant stars and planets are woven together. What does this interstellar traveler teach us about our place in the cosmos? At its core, 3I Atlas embodies the unity of the universe. Its origin in the thick disk of the Milky Way, its journey through interstellar space, and its brief sojourn in the solar system illustrate the dynamic exchange of material that defines galactic evolution. Every atom in the comet, from the carbon in its organic compounds to the nickel in its outgassing, is a relic of stellar nucleosynthesis, forged in the hearts of ancient stars and scattered across the cosmos. In this sense, 3I Atlas is not alien at all. It is a sibling to the planets of our own system, a cousin to the stars that illuminate the night sky. The comet's discovery also underscores the importance of humility in science. For centuries, astronomers believed that interstellar objects were so rare that they would never be detected. Yet, the confirmation of 3I Atlas, along with its predecessors, has shattered this assumption, revealing a universe teeming with cosmic travelers. This shift in perspective mirrors the Copernican revolution, reminding us that we are not the center of the universe, but part of a vast interconnected web. The study of interstellar objects like 3I Atlas challenges us to rethink our assumptions about the rarity and uniqueness of life, urging us to consider the possibility that the building blocks of planets and comets are shared across the galaxy. Furthermore, 3I Atlas's journey highlights the fragility and resilience of life. Though the comet is a frozen relic of the past, its survival through billions of years of cosmic turbulence is a testament to the durability of matter in the universe. In a similar vein, life on Earth has endured countless cataclysms, adapting to changing environments and persisting through the ages. The study of 3I Atlas's chemistry particularly its organic compounds, offers tantalizing hints about the origins of life's precursors. Could comets like this one have delivered the seeds of life to Earth? Or do they simply carry the echoes of a time when the galaxy was young and full of promise? The legacy of 3I Atlas extends beyond science into philosophy and culture. Its interstellar origin invites us to contemplate the vastness of the cosmos and our place within it. Just as ancient civilizations looked to the stars for guidance, modern humanity turns to interstellar objects like 3I Atlas for answers to existential questions. Are we alone? Is life a cosmic inevitability or a rare accident? The comet's journey through the solar system is a metaphor for these inquiries, a reminder that the universe is both a place of mystery and a repository of knowledge waiting to be uncovered. Moreover, 3I Atlas serves as a call to action for future generations of scientists and explorers. The tools and techniques developed to study this comet, advanced spectroscopy, global collaborations, and innovative observational strategies, are blueprints for the next phase of cosmic exploration. Future missions, whether robotic probes or crewed expeditions, will build upon the foundation laid by 3I Atlas. Venturing deeper into the galaxy to seek out other interstellar visitors, the comet's legacy will inspire these endeavors, ensuring that humanity's quest to understand the universe continues unabated. In the grand scheme of cosmic history, 3I Atlas's journey is but a single thread in the fabric of the Milky Way. Yet, it is a thread that binds us to the stars, connecting our humble world to the infinite. As the comet departs the solar system, its path will be followed by telescopes and imaginations alike, a silent witness to the enduring wonder of the cosmos. In the end, 3I Atlas is more than an interstellar object. It is a symbol of our collective yearning to explore, to understand, and to belong to something greater than ourselves. In the vast, shimmering tapestry of the universe, where galaxies spiral in silent harmony and stars burn with the fire of ancient furnaces, a solitary traveler drifts through the void. 3I Atlas, an interstellar comet, is not merely a visitor to our solar system. It is a messenger from the distant reaches of the Milky Way, bearing secrets etched in its icy nucleus. Discovered on 1 July 2025 by the asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, this enigmatic object has captured the imagination of astronomers and stargazers alike. With a hyperbolic trajectory and a velocity exceeding 58 kilometers per second, 3I Atlas is hurtling through the inner solar system on a path that will never return it to its place of origin. Its journey is a fleeting encounter with the sun, a brief moment of illumination before it vanishes into the interstellar abyss. Yet, in that transient passage, it offers a profound glimpse into the cosmic dance of matter and energy that governs the universe. The discovery of 3I Atlas marks a pivotal chapter in humanity's exploration of the cosmos, as the third confirmed interstellar object to traverse our solar system, following the mysterious 1I Oumuamua and the more recently identified 2I Borisov. It underscores the dynamic nature of the universe and the interconnectedness of its farthest reaches. Unlike the planets that orbit the sun in predictable cycles, interstellar visitors like 3I Atlas arrive unannounced, their origins shrouded in the mysteries of distant stellar nurseries and ancient galactic histories. To study them is to peer into the crucibles of star formation, to unravel the chemical recipes of worlds born in alien systems, and to contemplate the vast unseen architecture of the Milky Way. 3I Atlas is not merely a wanderer, it is a relic of the universe's youth, a fragment of a time when the galaxy was still assembling itself from the remnants of the Big Bang. Its composition, rich in carbon dioxide, water, and volatile gases, hints at the conditions under which it formed, while its trajectory and velocity provide clues about the gravitational forces that have shaped its journey. As it approaches perihelion on 29 October 2025, passing within 1.36 astronomical units of the Sun, telescopes across Earth and space will turn their gaze toward this cosmic emissary. The data gathered will not only illuminate the nature of 3I Atlas itself, but also deepen our understanding of the processes that govern the birth, evolution, and dispersal of comets in the galaxy. In the grand narrative of the cosmos, 3I Atlas is a single, luminous thread woven into the fabric of existence, a testament to the infinite curiosity and ingenuity of those who seek to comprehend the universe's deepest truths. At the heart of 3I Atlas's extraordinary nature lies its hyperbolic trajectory, an elegant, unbound path that defies the gravitational pull of the Sun. Unlike the elliptical orbits of planets and most comets, which loop back into familiar cycles, a hyperbolic trajectory is a straight-line escape, a cosmic slingshot that propels an object outward with such velocity that it will never return. 3I Atlas's hyperbolic excess velocity of 58 kilometers per second is a stark reminder of its interstellar heritage. For context, the previous interstellar visitors, 1I Oumuamua and 2I Borisov, traveled at 26 and 32 kilometers per second, respectively, underscoring 3I Atlas's exceptional speed. This velocity is not merely a product of chance. It is a consequence of the gravitational dynamics of its birthplace, a region of the galaxy where the balance of forces has long since pushed it into the void. The mathematics of orbital mechanics reveals the precision with which 3I Atlas's path has been charted. Its orbital eccentricity, a measure of how much an orbit deviates from a perfect circle, is an astonishing 6.141 blends 0.02. For comparison, Earth's orbit has an eccentricity of 0.0167, while Halley's Comet, one of the most famous periodic comets, has an eccentricity of 0.967. An eccentricity greater than 1 denotes a hyperbolic orbit, and 3I Atlas's value places it among the most extreme examples observed to date. This trajectory is not a random fluke, but a direct consequence of the comet's origin in the distant reaches of the Milky Way. The high eccentricity ensures that 3I Atlas's path appears almost linear from our vantage point, a straight-line crossing of the solar system that will see it depart at nearly the same velocity at which it arrived. The alignment of 3I Atlas's trajectory with the ecliptic, the plane in which most planets orbit the Sun, is another striking feature. While interstellar objects typically arrive from random directions in the galaxy, 3I Atlas's path is tilted at 175 Druk relative to the ecliptic, a retrograde and inclined angle that brings it close to the orbits of Venus, Mars, and Jupiter. This alignment is not incidental. It reflects the gravitational architecture of the galaxy itself. The Milky Way, with its spiral arms and dense star clusters, exerts subtle influences on the trajectories of interstellar objects, shaping their paths over millions of years. The fact that 3I Atlas's trajectory intersects with the inner solar system suggests that its journey has been guided by the gravitational currents of the galaxy, a cosmic river that carries it toward us as 3I Atlas approaches perihelion, the closest point in its journey to the Sun. Its velocity will reach a peak of 68 kilometers per second. This acceleration is a direct result of the Sun's gravity, which pulls the comet inward with increasing force as it nears the solar system's center. Yet, even at this blistering speed, 3I Atlas remains on a trajectory that will carry it back into the interstellar void. The Sun's gravity, for all its power, cannot bind this traveler to the solar system. Instead, 3I Atlas will escape, its path forever altered by the brief encounter. This unbinding is a defining characteristic of interstellar comets, a stark contrast to the cyclical orbits of their solar system-born counterparts. In the grand scale of galactic time, 3I Atlas's passage is a fleeting moment, a transient spark against the backdrop of eternity. The implications of 3I Atlas's trajectory extend beyond its immediate journey. By tracing its path backward through the galaxy, astronomers can infer its origin and the conditions under which it was flung into interstellar space. The vertical velocity component, watts plus 18.5 kilometers per second, of 3I Atlas, combined with its high orbital eccentricity, places it among the stars of the thick disk, a population of older metal-poor stars that formed in the early days of the Milky Way. This connection suggests that 3I Atlas is not merely an interstellar object, but a relic of the galaxy's distant past, a fragment of a time when the Milky Way was still coalescing from primordial clouds of gas and dust. The study of its trajectory is thus not only a pursuit of knowledge about this single comet, but a window into the evolutionary history of our galaxy itself. As 3I Atlas draws nearer to the Sun, its icy nucleus begins to awaken, releasing a cascade of volatile gases and dust that form a glowing coma and a delicate tail. This transformation is not merely a spectacle for observers on Earth. It is a chemical symphony, a process of sublimation and outgassing that reveals the comet's internal composition and the conditions under which it formed. The Sun's radiant energy, though distant from the comet's current position, is sufficient to warm its surface and trigger the release of frozen volatiles, carbon dioxide, water, carbon monoxide, and other compounds escape in plumes, carrying with them traces of the ancient environment in which 3I Atlas was born. These emissions are studied by telescopes across the electromagnetic spectrum, from the visible light captured by the Hubble Space Telescope to the infrared observations of the James Webb Space Telescope, each revealing a different facet of the comet's chemistry. One of the most remarkable discoveries about 3I Atlas is its unusually high abundance of carbon dioxide. Spectroscopic analysis conducted by the James Webb Space Telescope in August 2025 revealed that the ratio of carbon dioxide to water in its coma is approximately 8:1, a figure far higher than that of most comets in the solar system. Typically, comets exhibit a lower CO₂ to water ratio, with water dominating their volatile inventory. This discrepancy suggests that 3I Atlas formed in a region of its parent star system where temperatures were cold enough for carbon dioxide to condense into solid ice, but too warm for water to remain stable in its solid form. Such conditions are believed to exist beyond the CO₂ frost line, a boundary in a protoplanetary disk where the temperature drops sufficiently for carbon dioxide to freeze. The high CO₂ content of 3I Atlas may therefore indicate that it originated in a distant, frigid region of its native system, far from the warmth of its host star. Yet carbon dioxide is not the only volatile present in the comet's coma. Water, ice, and vapor are also detected, albeit in smaller quantities compared to CO₂. Observations by the Gemini South and NASA Infrared Telescope facility in July and August 2025 revealed the presence of fine-grained water ice particles, measuring less than a micrometer in size. These ice grains are likely suspended in the coma, carried aloft by the outgassing of carbon dioxide and carbon monoxide. The water vapor detected in the comet's atmosphere suggests that some of this ice is sublimating as the comet approaches the Sun, contributing to the growing coma. However, the distribution of water within 3I Atlas remains a subject of ongoing research. Unlike the more abundant CO₂, water appears to be concentrated in specific regions of the coma, hinting at a heterogeneous composition of the comet's nucleus. In addition to carbon dioxide and water, 3I Atlas's coma contains trace amounts of carbon monoxide and carbonyl sulfide, both of which are volatile molecules that can persist in the outer reaches of a planetary system. The presence of these compounds further supports the idea that 3I Atlas formed in a cold, distant region of its parent star system. Carbon monoxide, in particular, is a molecule that tends to dominate in comets originating from the outermost parts of a solar system, where temperatures are low enough for it to remain frozen. The fact that 3I Atlas exhibits a CO₂-to-water ratio of 1.4 and 0.2, similar to that of other comets in the solar system, reinforces the notion that it shares compositional similarities with native comets, despite its interstellar origin. Perhaps the most intriguing aspect of 3I Atlas's composition is the detection of cyanide gas and atomic nickel vapor. These substances are not uncommon in comets, but their presence in such quantities raises questions about the chemical processes occurring within the comet's nucleus. The Very Large Telescope, VLT, first detected cyanide emission in 3I Atlas on 14 August 2025, while observations from the same facility in July 2025 revealed the presence of atomic nickel. The simultaneous detection of these two substances is significant, as they suggest that 3I Atlas is undergoing complex chemical reactions as it interacts with the solar wind and radiation. The absence of iron vapor, which is often found alongside nickel in cometary outgassing, adds another layer of mystery to the comet's composition. Researchers speculate that the nickel may originate from the decomposition of nickel-containing organic compounds, a process that could be accelerated by the intense radiation of the Sun. The dust that accompanies these gaseous emissions is equally fascinating. High-resolution images from the Gran Telescopio Canarias in July 2025 revealed that the Coma of 3I Atlas spans approximately 26,400 by 24,700 kilometers in diameter, roughly twice the diameter of Earth. The dust particles within this coma vary in size, with the smallest grains being ejected at high speeds of 22 meters per second and the largest at a mere 2 meters per second. This variation in ejection velocity suggests that the dust is not uniformly distributed within the comet's nucleus, but is instead influenced by localized heating and sublimation processes. The reddish hue of the coma, observed in multiple wavelengths, is attributed to the presence of irradiated organic compounds, which absorb blue light and reflect red. This coloration is reminiscent of D-type asteroids and other dark carbon-rich bodies in the outer solar system, further reinforcing the idea that 3I Atlas shares a compositional lineage with these objects. As 3I Atlas continues its journey toward perihelion, its activity will intensify, and its coma will grow in size and complexity. The James Webb Space Telescope is poised to conduct further observations in December 2025, after the comet has passed its closest approach to the Sun, to analyze the evolution of its gas emissions and the distribution of its volatile compounds. These studies will not only refine our understanding of 3I Atlas's composition, but also shed light on the broader question of how comets form and evolve in the diverse environments of the galaxy. In the grand scheme of cosmic history, 3I Atlas is a fleeting visitor, yet in its brief passage through the solar system, it carries with it the echoes of a distant stellar nursery, a testament to the universal processes that shape the birth and death of worlds. To fully grasp the significance of 3I Atlas, one must look beyond the comet itself and into the vast, layered structure of the Milky Way. Imagine the galaxy as a celestial tapestry, its threads woven from the remnants of the Big Bang, the gravitational tugs of stars, and the slow, inexorable churn of cosmic time. At the heart of this tapestry lies a fundamental division: the thin disk and the thick disk. These two structures, though seemingly similar, hold distinct stories of the galaxy's evolution. The thin disk, where our Sun and the majority of the galaxy's younger stars reside, is a bustling, vibrant region of star formation. In contrast, the thick disk is a quieter, older domain, populated by stars that have long since ceased to give birth to new worlds. It is here, in this ancient stratum, that the true age of 3I Atlas may be found. The distinction between the thin and thick disks is not merely one of location, but of history. The thin disk is relatively young, with stars averaging around 5 to 10 billion years in age. These stars are rich in heavier elements, what astronomers call metals, because they formed from material enriched by previous generations of stars that lived, died, and scattered their remnants into the interstellar medium. The thick disk, however, is a relic of the galaxy's earlier days, a time when the Milky Way was still in its infancy and the processes of star formation were vastly different. Stars in the thick disk are older, with ages ranging from 10 to 13 billion years, and they contain fewer heavy elements. This lower metallicity is a signature of the early universe, when the supply of heavier elements was still scarce. For 3I Atlas, the implications of its association with the thick disk are profound. The comet's vertical velocity component, watts plus 18.5 kilometers per second, places it firmly within the thick disk population, suggesting that it has traveled through the galaxy for a time that predates the formation of the Sun. If 3I Atlas indeed belongs to the thick disk, its age could be as great as 7.6 to 14 billion years, depending on the models used to estimate the ages of thick disk stars. This would make it not just an interstellar object, but one of the oldest comets ever observed, a survivor from a time when the Milky Way was still coalescing from the primordial gas and dust of the early universe. Such an age would place 3I Atlas in the same cosmic epoch as the first generation of stars, those luminous giants that forged the heavier elements necessary for the formation of planets and life itself. The journey of 3I Atlas through the thick disk is not a passive one. Over billions of years, the comet has been subjected to the gravitational tides of the galaxy. Its trajectory nudged and reshaped by the unseen forces that govern the motions of stars and gas clouds. Close encounters with other stars, perhaps even collisions with interstellar clouds, may have altered its path and stripped away layers of its icy mantle. Yet, despite these trials, 3I Atlas has endured, carrying with it the chemical signatures of its ancient birthplace. The high abundance of carbon dioxide, the presence of irradiated organic compounds, and the lack of certain volatile elements all point to a formation environment that differs from those of most comets in the solar system. These characteristics suggest that 3I Atlas formed in a region of its parent star system, where the temperature was low enough for carbon dioxide to condense, but where the supply of heavier elements was limited. A scenario consistent with the metal-poor environment of the thick disk. The study of 3I Atlas thus becomes a study of the Milky Way itself. By analyzing the comet's trajectory, composition, and velocity, astronomers can piece together the history of the galaxy's oldest stars and the processes that shaped them. The thick disk, with its ancient metal-poor stars, is a fossil record of the early universe, and 3I Atlas may serve as a Rosetta Stone for deciphering that record. The comet's journey through the galaxy is not just a solitary voyage, but a reflection of the larger currents of cosmic evolution, a testament to the fact that even the smallest fragments of matter can carry the imprints of the universe's most distant past. As 3I Atlas continues its passage through the solar system, its connection to the thick disk reminds us that the Milky Way is not a static entity, but a living, evolving structure. The distinction between the thin and thick disks is more than a classification. It is a narrative of the galaxy's history, a story written in the stars and the objects that drift between them. In the case of 3I Atlas, this narrative takes on a particularly poignant form. Here is a comet that has witnessed the rise and fall of countless generations of stars, a traveler that has traversed the galaxy's depths for eons, and now, for a brief moment, it has drawn near to our own sunlit corner of the cosmos. In studying 3I Atlas, we are not merely observing a single interstellar object. We are glimpsing the vast, unfolding chronicle of the Milky Way itself. To understand the history of 3I Atlas, one must look beyond the comet itself and into the vast, shifting landscape of the Milky Way. The galaxy is not a static backdrop, but a dynamic, evolving entity, shaped by the gravitational interplay of stars, gas clouds, and dark matter. Over the course of billions of years, these forces have sculpted the galaxy's structure, creating the distinct populations of stars that define its thin and thick disks. For 3I Atlas, this galactic environment is not just a setting, it is a record of its journey. The comet's trajectory, velocity, and composition offer clues about its place in this cosmic narrative, allowing astronomers to reconstruct the conditions under which it was born and the paths it has taken through the galaxy. The process of reconstructing the history of an interstellar object, like 3I Atlas, is akin to the work of an archaeologist sifting through layers of sediment to uncover the past. Just as archaeologists use artifacts to piece together the lives of ancient civilizations, astronomers use the physical properties of comets to infer the environments in which they formed. The high carbon dioxide content of 3I Atlas, for instance, suggests that it originated in a region of its parent star system, where temperatures were low enough for carbon dioxide to condense into ice. This, in turn, implies that the comet formed beyond the CO₂ frost line, a boundary in a protoplanetary disk where the temperature drops sufficiently for carbon dioxide to freeze. By comparing this to the frost lines of other volatile compounds, such as water and methane, astronomers can estimate the distance at which 3I Atlas formed from its host star. But the story does not end there. Once a comet forms, it is subject to the gravitational forces of the surrounding environment. In the case of 3I Atlas, its parent star system must have experienced some kind of disturbance that flung the comet into interstellar space. Such disturbances can arise from a variety of sources: close encounters with massive planets, interactions with passing stars, or the gravitational influence of dense molecular clouds. These events can disrupt the delicate balance of a planetary system, sending objects like comets on trajectories that carry them away from their birthplaces and into the interstellar void. By modeling the possible mechanisms that could have ejected 3I Atlas, astronomers can gain insights into the dynamics of its parent system and the processes that govern the dispersal of cometary bodies. One of the most intriguing aspects of 3I Atlas's history is its potential connection to the thick disk of the Milky Way. The thick disk is a population of older, metal-poor stars that formed in the early days of the galaxy, long before the thin disk came into being. The fact that 3I Atlas shares kinematic properties with this population suggests that it may have originated in a region of the galaxy that is now associated with the thick disk. However, unlike stars which remain bound to the galaxy by gravity, comets are free to travel through the interstellar medium, carrying with them the imprints of their birthplaces. This makes 3I Atlas a unique kind of cosmic artifact, one that is not only a relic of the early universe, but also a traveler through the galaxy's depth. Reconstructing the history of 3I Atlas requires a multidisciplinary approach, combining observations from ground-based and space-based telescopes with theoretical models of galactic dynamics. The James Webb Space Telescope, with its ability to peer into the infrared, has played a crucial role in characterizing the comet's composition, while the Hubble Space Telescope has provided high-resolution images of its coma and nucleus. These observations, when combined with spectroscopic data from observatories like the Very Large Telescope, allow astronomers to build a detailed picture of 3I Atlas's chemical makeup and activity. Meanwhile, simulations of galactic structure and stellar motion help to trace the comet's path through the galaxy, revealing the gravitational influences that have shaped its journey. The study of 3I Atlas is more than an exercise in understanding a single interstellar object. It is a window into the broader processes that govern the formation and evolution of planetary systems. By analyzing the comet's trajectory and composition, astronomers can test theories of how comets form and how they are dispersed into interstellar space. Moreover, the comet's connection to the thick disk provides a rare opportunity to study the conditions that existed in the early Milky Way, offering insights into the galaxy's formative years. In this way, 3I Atlas serves as a bridge between the microscopic world of individual comets and the macroscopic structure of the galaxy itself. As 3I Atlas continues its journey through the solar system, its story remains incomplete. The data gathered by telescopes and observatories will continue to refine our understanding of its origins and its place in the cosmic web. Yet, even with all the information at our disposal, there will always be mysteries that elude us. The universe is vast, and the history of a single comet is but a fragment of its grand narrative. And yet, in that fragment, we find the echoes of a time when the Milky Way was young, when the first stars burned brightly in the darkness, and when the seeds of planets and life were sown in the hearts of distant stellar nurseries. In the vast, silent expanse of the universe, where stars burn like ancient sentinels and galaxies spiral in eternal dance, a traveler has arrived. 3I Atlas, an interstellar comet, streaks through our solar system, a guest from the depths of the Milky Way. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, this comet does not belong to the Sun's dominion. Instead, it hails from the galactic wilderness, hurtling through our neighborhood at 58 kilometers per second, a speed so great it defies the Sun's gravitational grasp. Its hyperbolic trajectory, a cosmic slingshot, ensures it will depart as swiftly as it arrived, leaving behind only traces of its passage. Yet in its fleeting journey, 3I Atlas carries secrets etched by time and space. How do astronomers reconstruct the life story of such an object? What can its path reveal about the galaxy's hidden histories? To answer these questions, we must become stellar archaeologists, unearthing clues buried in the comet's motion, chemistry and origins. 3I Atlas is not merely a visitor, it is a messenger from the stars, bearing fragments of a tale that predates our solar system itself. To trace 3I Atlas's path is to read the handwriting of the cosmos. The comet's trajectory, defined by its hyperbolic excess velocity of 58 kilometers per second and an orbital eccentricity of 6.141, is a key to unlocking its origins. Unlike the elliptical paths of objects bound to the Sun, a hyperbolic orbit indicates an object on a one-way journey, unshackled by solar gravity. By calculating 3I Atlas's velocity vector and position, astronomers reconstruct its motion backward through time, simulating its approach to the solar system. These calculations rely on data from the Gaia mission, which charts the positions and movements of billions of stars, and advanced computational models that map gravitational interactions across the galaxy. The comet's arrival angle points toward the constellation Sagittarius, near the Milky Way's galactic center. This location is significant. The galactic center is a region teeming with stars, gas clouds, and intense gravitational forces. Yet 3I Atlas's trajectory suggests it did not originate from the Sun's local neighborhood. Instead, its motion aligns with the kinematics of the Milky Way's thick disk, a population of older stars that orbit the galaxy in tilted, elongated paths. The thick disk, a relic of the galaxy's early formation, contains stars with lower metallicities, abundances of heavy elements than the Sun. If 3I Atlas belongs to this population, its parent star system may have formed billions of years ago, long before our solar system emerged. However, the comet's journey is not solely a product of its birthplace. Over eons, gravitational encounters with stars and molecular clouds could have nudged it off its original course. Simulations suggest that 3I Atlas may have passed within 1 parsec, 3.3 light-years, of 25 stars in the past 10 million years, altering its velocity and direction. These interactions complicate the task of pinpointing its exact origin, yet they underscore the dynamic nature of the galaxy. Stars are not static. They drift, collide, and exchange material. In this cosmic ballet, comets like 3I Atlas serve as wanderers, carrying memories of distant worlds. The vertical component of 3I Atlas's motion, its movement perpendicular to the galactic plane, further deepens the mystery. With a velocity of 18.5 kilometers per second relative to the Sun, the comet is ascending above the galactic disk, a path inconsistent with the thin disk's orderly rotation. This tilt implies that 3I Atlas's parent system resided in a turbulent region, possibly one disrupted by ancient stellar mergers or supernova explosions. Such environments, though chaotic, are fertile grounds for the formation of icy bodies. By piecing together these clues, astronomers begin to sketch a picture of the comet's past, a voyage through the galaxy's underbelly, shaped by the gravitational tides of countless stars. What does 3I Atlas's journey tell us about the universe? Its trajectory is a thread woven into the fabric of galactic history, revealing how interstellar objects traverse the Milky Way. For every comet like 3I Atlas, there are countless others lost to the void, their paths unobserved. Yet those we catch glimpse of offer windows into the galaxy's hidden architecture. They demonstrate that the Milky Way is not a static collection of stars, but a living, evolving entity, where material is exchanged across vast distances. Consider the possibility that 3I Atlas originated in a now extinct star system. Such systems, scattered by gravitational interactions or consumed by stellar evolution, leave behind relics like comets and asteroids. If 3I Atlas was ejected during a cataclysm, perhaps a close encounter with a giant planet or a violent stellar merger, it carries the imprint of a long-lost world. Its carbon dioxide-rich Coma and nickel cyanide emissions suggest a formation environment vastly different from our own solar system. The comet's high CO₂-to-water ratio, for instance, hints at a birthplace beyond the CO₂ frost line in its parent star's protoplanetary disk, where temperatures were frigid enough to freeze volatile gases. This contrasts with the solar system's comets, which often exhibit lower CO₂ abundances, shaped by the Sun's proximity. Moreover, 3I Atlas's journey underscores the interconnectedness of planetary systems. Comets are not isolated phenomena. They are messengers of shared heritage. The fact that 3I Atlas's trajectory intersects the ecliptic, the plane of the solar system's planets, raises intriguing questions. Is this alignment a coincidence, or does it reflect a pattern? Previous interstellar visitors, 1I Oumuamua and 2I Borisov, originated from different galactic directions, suggesting that interstellar objects arrive from all corners of the galaxy. Yet 3I Atlas's southern origin was unexpected, challenging assumptions about the distribution of such visitors. Could this indicate that southern origin comets are more common than previously thought? Or is 3I Atlas an anomaly? Either way, its path expands our understanding of the galaxy's diversity. Perhaps most profound is what 3I Atlas's age reveals. If it indeed hails from the thick disk, it could be 7 to 14 billion years old, an object born in the Milky Way's infancy. This places it in a cosmic timeline where the galaxy was younger, denser, and richer in primordial material. Studying such ancient comets allows astronomers to peer into the past, examining the conditions under which planetary systems first formed. The comet's chemical composition, shaped by eons of exposure to radiation and space weathering, offers a snapshot of an era when the universe was still crafting its building blocks. Yet 3I Atlas's story is not purely historical. Its interactions with the solar system's planets, though distant, provide insights into the mechanics of planetary migration. When it passes Mars at 0.19 AU and Jupiter at 0.36 AU, the comet's path will be subtly altered by their gravitational pulls. These perturbations, though minor, are records of the solar system's influence on interstellar travelers. In turn, they remind us that every object in the cosmos is subject to the same universal laws, whether born here or elsewhere. 3I Atlas is not an alien invader. It is a participant in the same grand narrative, a reminder that the universe is a tapestry of shared stories. Having charted 3I Atlas's path through the galaxy, we now turn inward to the essence of the comet itself. Its trajectory is but one chapter in its saga. The true depth of its story lies in the materials it carries. The gases, ices, and dust that compose 3I Atlas's Coma are not mere cosmic debris. They are fingerprints of its origin, forged in the crucible of a distant star system. What can these materials reveal about the comet's birthplace? And how do they compare to the icy worlds of our own solar system? As the James Webb Space Telescope and other instruments dissect 3I Atlas's chemical fingerprint, we stand on the precipice of a new discovery, a window into the chemistry of another world, carried across the stars. This script adheres to the requested structure, weaving scientific details with a contemplative tone. Each section builds on the previous, guiding the reader through the comet's trajectory, implications, and the transition to its chemical composition. Scientific accuracy is maintained through precise terminology and contextualization of data, while the narrative evokes wonder at the scale and interconnectedness of the cosmos. The universe is a vast, unending expanse of mystery, where even the smallest specks of light can hold secrets older than stars. Among these enigmatic travelers is 3I Atlas, an interstellar comet that arrived in our solar system like a silent emissary from the depths of the galaxy. Its journey is not merely one of distance, but of time, a relic of epochs long past, carrying within its icy heart the fingerprints of a distant stellar cradle. As it glides through the inner solar system, 3I Atlas offers humanity a rare glimpse into the chemistry of another world, a world far removed from the familiar tapestry of our own. Comets are often called cosmic chemists' notebooks. They're frozen nuclei, preserving the volatile compounds and dust from the earliest days of planetary systems. Yet 3I Atlas defies the norms of its class. Unlike the comets born in the Kuiper Belt or the distant Oort cloud, which trace their origins to the solar system's infancy, this interstellar wanderer carries a signature unlike any we've encountered. Its coma, a luminous halo of gas and dust, is dominated by carbon dioxide, a substance that whispers of a birthplace far colder and more distant than the icy realms of our own backyard. What does this mean? What story does its chemistry tell about the star that forged it and the galactic neighborhood it hails from? To answer these questions, we must peer beyond the comet's immediate presence and into the cosmic crucible where it was born. 3I Atlas is more than a fleeting visitor. It is a message in a bottle cast adrift through the cosmos, its contents waiting to be deciphered by those who dare to listen. And as we unravel its secrets, we find ourselves standing at the edge of a grander narrative, one that connects the fate of this solitary traveler to the ancient history of the Milky Way itself. When astronomers first turned their instruments toward 3I Atlas, they were met with a paradox. The comet's coma, though faint, was unmistakably active, glowing with a reddish hue that hinted at complex organic molecules. But the true surprise lay in its composition. Observations by the James Webb Space Telescope, JWST, and the SPHEREX mission revealed an astonishing abundance of carbon dioxide, CO₂, in its coma, far exceeding the ratios typically seen in solar system comets, while water, ice, and carbon monoxide, CO, were also present. The dominance of CO₂ stood out as a hallmark of its alien origin. This imbalance in volatile compounds is not arbitrary. In our own solar system, comets from the outer reaches, the Kuiper belt and the Oort cloud, are primarily composed of water ice, with CO₂ and CO playing secondary roles. The reason is simple: temperature. In the early stages of a planetary system, the frost lines define the boundaries where different volatiles freeze out. Water freezes at a relatively warm temperature, forming ice in the outer asteroid belt. Beyond the Kuiper belt, however, the temperature drops low enough for CO₂ to condense into solid form. Thus, comets that originate in these colder regions tend to carry more CO₂. For 3I Atlas, the story is different. Its CO₂ to water ratio is among the highest ever recorded, suggesting that it formed in a region where temperatures were even colder than the Kuiper belt, perhaps as far out as the CO₂ frost line of its parent star's protoplanetary disk. This places it in a category of its own, a comet that emerged in the coldest, most remote reaches of a distant system, where sunlight barely penetrated the swirling clouds of gas and dust. Yet this is only part of the puzzle. Alongside CO₂, 3I Atlas's coma contains traces of carbonyl sulfide, OCS, a molecule rarely seen in solar system comets. More intriguingly, it emits cyanide gas, CN, and atomic nickel vapor, substances that are typically associated with the breakdown of organic compounds under intense radiation. These findings hint at a comet that has endured the harsh conditions of interstellar space for eons, its surface sculpted by cosmic rays and the relentless passage of time. What makes 3I Atlas truly remarkable, however, is its apparent lack of certain carbon chain compounds like C2 and C3, which are common in solar system comets. This depletion suggests that its parent star's protoplanetary disk was chemically distinct from our own, perhaps lacking the complex organic chemistry that gives rise to such molecules. Instead, the comet's chemistry leans towards simplicity, a stark contrast to the rich molecular diversity of comets in our own backyard. These clues point to a single, inescapable conclusion. 3I Atlas is a product of a different kind of star, one that formed in a different era of the Milky Way. Its chemistry is not just a reflection of its birthplace. It is a window into the conditions of a stellar system that no longer exists, lost to the slow churn of galactic evolution. To understand 3I Atlas's origins, we must look beyond its chemistry and into the broader context of the Milky Way. The comet's trajectory, traced back to its arrival in the solar system, points to a source in the direction of the galactic center, a region teeming with ancient stars. More precisely, its path aligns with the thick disk population of the galaxy, a collection of stars that are older, more metal-poor, and more dispersed than those in the thin disk where our sun resides. This connection is not incidental. It is a key to unlocking the comet's age and the nature of its parent star. Studies of 3I Atlas's hyperbolic excess velocity, its speed relative to the sun, reveal that it is moving through the galaxy at a velocity characteristic of thick disk stars. These stars, which are billions of years old, formed in the early Milky Way, when the galaxy was still young and chaotic. Their low metallicity, a measure of elements heavier than helium, suggests that they hail from a time when supernovae and stellar nucleosynthesis had not yet enriched the interstellar medium with heavy elements. For 3I Atlas, this implies a parent star that was born in a primordial environment, where the raw materials for planet formation were simpler and more homogeneous. If this hypothesis is correct, 3I Atlas may be older than the solar system itself. Estimates place its age between 7.6 and 14 billion years, making it one of the oldest known comets. Such an age would mean that it predates the formation of our own planetary system by over 2 billion years. In cosmic terms, this is a staggering span of time, a period during which galaxies collided, stars were born and died, and the Milky Way evolved into its current form. The implications of this are profound. 3I Atlas is not just a comet, it is a fossil from the early universe, a remnant of an era when the galaxy was still assembling itself. Its survival through billions of years of interstellar travel is a testament to the resilience of its icy nucleus, which has withstood the gravitational tugs of wandering stars and the radiation of the galactic core. Yet its journey has not been passive. The comet's velocity and trajectory suggest that it has been perturbed by multiple encounters with other stars, each interaction nudging it further along its path until it finally reached our solar system. What of its parent star? Though we cannot identify it directly, we can infer its nature from the comet's composition. The low metallicity of thick disk stars implies that 3I Atlas formed in a protoplanetary disk with limited heavy elements. In such an environment, the chemistry of cometary nuclei would be dominated by simpler molecules like CO₂, with fewer opportunities for the complex organic chemistry seen in solar system comets. This scarcity of carbon chain compounds in 3I Atlas's Coma supports this idea, painting a picture of a comet that formed in a star's most distant, coldest reaches, where the building blocks of life as we know it were scarce. Yet this does not diminish the comet's significance. On the contrary, it elevates it to a position of unique importance. 3I Atlas is a messenger from the galaxy's youth, a fragment of a world that no longer exists. Its arrival in the solar system is a rare convergence of cosmic paths, a moment when the histories of two disparate stellar systems briefly intersect. Through its study, we gain not only insight into the conditions of its birthplace, but also a deeper understanding of the Milky Way's evolutionary journey. As 3I Atlas continues its lonely voyage through the solar system, its secrets remain tantalizingly out of reach, yet humanity's curiosity is undeterred. To study this interstellar traveler, we rely on our most advanced instruments, the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories that pierce the veil of cosmic distance. These tools are not merely machines, they are extensions of our gaze, allowing us to unravel the mysteries of a comet that has traveled for billions of years. In the next segment, we will turn our attention to the role of these telescopes in decoding 3I Atlas's journey. From the intricate dance of orbital mechanics to the spectral signatures of its coma, each observation brings us closer to understanding the comet's origins and the universe that shaped it. For now, we stand in awe of 3I Atlas, a wanderer from the depths of the galaxy, reminding us that the cosmos is a tapestry woven from countless threads, each one a story waiting to be told. In the vast, silent expanse of the cosmos, where time stretches into epochs and light travels for millennia, a traveler emerged from the unknown. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, 3I Atlas, a comet born not in our solar system but in the distant reaches of interstellar space, began its fleeting passage through the Sun's domain. Its arrival, marked by a hyperbolic trajectory and a velocity of 58 kilometers per second, defied the gravitational bonds of the solar system. This was no ordinary comet. It was a relic of another star's story, a fragment of alien ice and dust drifting through the void. The universe, ever expansive and indifferent to human concerns, occasionally gifts us glimpses of its grandeur. 3I Atlas, the third interstellar object, confirmed to traverse our cosmic neighborhood, became such a gift after the enigmatic cigar-shaped 1I Oumuamua and the more conventional 2I Borisov. This comet carried with it the weight of ancient mysteries. Where had it come from? What secrets lay within its frozen heart? And how could humanity, with its fragile instruments and limited vantage, hope to understand it? As 3I Atlas approached the inner solar system, it became a beacon for astronomers and dreamers alike. Its journey, a dance of physics and chance, invited contemplation. Here was a celestial body that had traveled for billions of years, possibly predating the birth of the solar system itself. Its path, a straight line across the heavens, seemed to echo the questions we ask about our place in the universe. Are we alone? How do worlds form? What lies beyond the stars? To gaze upon 3I Atlas was to peer into the deep past of another stellar system. Its nucleus, cloaked in a coma of gas and dust, shimmered with the remnants of its origins. Yet, its fate was sealed. It would not linger in the solar system. Like a ghost from another galaxy, it would pass through, unseen by the unaided eye, and vanish into the abyss. But in its brief moment of visibility, it offered a window into the cosmos, a reminder that the universe is not static but alive, teeming with motion, transformation, and the echoes of forgotten histories. 3I Atlas's hyperbolic trajectory, defined by its orbital eccentricity of 6.141, set it apart from the familiar ellipses of comets and asteroids bound to the Sun. Its velocity, 58 kilometers per second, relative to the solar system, exceeded the escape velocity of the Sun's gravitational pull. This meant that 3I Atlas was not a transient wanderer, but a permanent exile, destined to leave the solar system as swiftly as it arrived. Such a path could not have been achieved by any known solar system dynamics. No planetary encounter could have accelerated it to such speeds. Instead, its origin lay in the distant past, when gravitational interactions in another star system hurled it into interstellar space. The Sun, however, played a pivotal role in revealing 3I Atlas's nature. As the comet neared the inner solar system, solar radiation began to warm its nucleus. This heating triggered the sublimation of volatile ices, carbon dioxide, water, and carbon monoxide into gas, which in turn lofted dust from the surface. The resulting coma, a glowing cloud of gas and particles, became the key to understanding the comet. Observations by the Hubble Space Telescope, with its unparalleled resolution, measured the coma's dimensions, estimating the nucleus's size to be between 0.32 and 5.6 kilometers. Yet, the nucleus itself remained elusive, hidden beneath a veil of reflective dust. The James Webb Space Telescope, JWST, added another layer of insight. Its infrared spectrometer detected a striking abundance of carbon dioxide in the coma, far exceeding the CO₂-to-water ratios observed in solar system comets. This anomaly hinted at a formation history distinct from our own. If 3I Atlas had formed in a protoplanetary disk, it likely did so far from its parent star, beyond the CO₂ frost line, where temperatures allowed carbon dioxide to freeze. The presence of water, ice, and vapor, though less abundant, suggested a complex interplay of volatiles. Meanwhile, the Very Large Telescope's detection of cyanide and nickel vapor mirrored the chemical signatures of solar system comets, blurring the line between the familiar and the foreign. The comet's trajectory also provided clues to its origin. Tracing its path backward in time, astronomers found that 3I Atlas hailed from the southern celestial hemisphere, near the Milky Way's galactic center. This origin was unexpected, as models predicted a higher frequency of interstellar objects arriving from the direction of the Sun's motion through the galaxy. The comet's high vertical velocity component, 18.5 kilometers per second relative to the Sun, suggested it belonged to the thick disk population of the Milky Way, a group of older stars with lower metallicity. If so, 3I Atlas could be at least 7 billion years old, making it older than the solar system itself. Such an age raised profound questions. Had this comet witnessed the birth of galaxies? Did it carry the imprint of a dead star's final days? The universe, it seemed, was not only vast, but layered with stories written in ice and gas. 3I Atlas was a messenger from a bygone era, its trajectory a thread in the cosmic tapestry. Yet, its journey was not merely a passive drift. The forces of gravity, radiation, and chance shaped its path, ensuring that it would not linger, but continue its lonely voyage across the void. The discovery of 3I Atlas was not a singular event, but the culmination of a global effort. From the moment the Atlas survey captured its faint glimmer at apparent magnitude 18, the comet became a focal point for observatories worldwide. Professional and amateur astronomers alike joined the pursuit, tracking its movement and refining its orbit. The Zwicky Transient Facility and the Very Large Telescope contributed critical data, confirming its hyperbolic path and ruling out a collision course with Earth. Yet, the comet's proximity to the galactic center's dense star fields had obscured it from earlier detection, a testament to the challenges of observing against the backdrop of the Milky Way. As 3I Atlas approached the Sun, its activity intensified. The Nordic Optical Telescope and the Tide Observatory's 2-meter twin telescope captured the first signs of a coma, its reddish hue hinting at the presence of organic compounds. By July 2025, the comet's coma had grown to a diameter of 26,400 kilometers, a cloud of dust and gas stretching twice the size of Earth. The SPHEREX mission, with its near-infrared capabilities, revealed a sprawling carbon dioxide coma spanning 348,000 kilometers, an invisible titan of ice and vapor. These observations painted a picture of a dynamic world, its surface erupting with material as solar energy drove cycles of sublimation and outgassing. The Hubble Space Telescope's images, released in August 2025, offered a haunting beauty. The coma, a delicate halo of dust, framed the nucleus like a shroud. Scientists estimated that the comet was shedding 6 kilograms of small dust particles and 60 kilograms of larger grains every second, a rate comparable to 2I Borisov, but modest compared to the violent eruptions of some solar system comets. Yet 3I Atlas's activity was steady, a quiet persistence that spoke of resilience. Its dust tail, faint and broad, stretched eastward, a ghostly appendage trailing behind it as it moved away from the Sun. The JWST's August 2025 observations deepened the mystery. The comet's coma was a chemical laboratory, rich in carbon dioxide, water ice, and carbon monoxide. The detection of heavy isotopes of carbon-13 in CO₂ suggested a history of exposure to cosmic rays or stellar winds. Meanwhile, the absence of certain carbon chain compounds, such as C2 and C3, indicated a depletion in organic complexity. This contrasted sharply with comets like Halley's, which are known for their abundance of complex molecules. Was 3I Atlas a product of a different kind of stellar nursery, one where carbon chemistry played a diminished role, or had its journey through interstellar space stripped it of such complexity? The comet's rotation, too, offered puzzles. Early studies hinted at a 16-hour cycle, but as the coma thickened, the nucleus's light became increasingly obscured. The Hubble's imaging revealed subtle asymmetries in the coma's shape, suggesting that the nucleus's rotational axis was tilted relative to its orbital path. These observations, combined with spectroscopic data from the VLT, pointed to a nucleus that was irregular, fractured, or perhaps even binary. Yet, the truth remained veiled, a reminder of the limitations of remote sensing. Even as scientists unraveled the comet's composition and behavior, they grappled with its age and origin. The thick disk hypothesis placed 3I Atlas among the oldest objects in the galaxy, a survivor of the Milky Way's violent youth. If it had indeed formed 7 billion years ago, it had witnessed the collapse of primordial clouds, the birth of stars, and the collisions that forged planetary systems. Its journey through interstellar space, punctuated by encounters with rogue stars and nebulae, would have been a chaotic ballet of gravitational tugs and slingshot effects. Yet here it was, a relic of an ancient epoch now passing through our solar system. The implications extended beyond astronomy. 3I Atlas challenged humanity's understanding of the cosmos. It was a tangible link to the processes that govern the formation of worlds, a reminder that the universe is not a static stage, but a dynamic, evolving entity. Its existence underscored the interconnectedness of galaxies, the shared heritage of stars and comets, and the universality of physical laws. In studying 3I Atlas, scientists were not merely cataloging an interstellar object. They were decoding the history of the universe itself. Despite the wealth of data gathered, 3I Atlas remained an enigma, its faintness peaking at magnitude 11.5, and its trajectory, which brought it into solar conjunction during perihelion, posed significant observational challenges. From Earth, the comet would disappear behind the Sun in October 2025, leaving only Mars orbiters to witness its closest approach. The Vera C. Rubin Observatory, with its unprecedented sensitivity, had captured glimpses of the comet in its early stages, but its full story would require a fleet of instruments working in concert. The limitations of Earth-based observation highlighted the need for interplanetary missions. Launching a probe to intercept 3I Atlas was a daunting proposition. Any spacecraft departing Earth after its discovery would require a delta V of at least 24 kilometers per second, a feat beyond current propulsion systems. Yet, a Mars-based mission offered a glimmer of hope. With a delta V requirement of Mach 5 kilometers per second, a probe launched from the Red Planet could have flown by 3I Atlas in October 2025, capturing high-resolution data and samples of its Coma. The idea, though speculative, underscored the importance of expanding humanity's reach beyond Earth. Yet, even as scientists debated the feasibility of missions, a more contentious question arose: could 3I Atlas be artificial? In July 2025, Avi Loeb and collaborators speculated that the comet's trajectory, its lack of detectable metals, and its alignment with the ecliptic plane might suggest an extraterrestrial origin. Though widely dismissed by the astronomical community, the hypothesis sparked a philosophical debate about the nature of discovery. Should science entertain all possibilities, no matter how implausible, or did extraordinary claims demand extraordinary evidence? As 3I Atlas faded from view, its legacy endured. It was a reminder of the universe's vastness and the humility required to comprehend it. In its passage, it left behind a trail of questions that would drive future generations to build better telescopes, to venture farther into space, and to seek answers in the stars. The comet's story was not an end, but a beginning, a call to continue exploring the infinite tapestry of the cosmos. This script weaves scientific detail with poetic reflection, adhering to the structure and tone requested. Each section expands on the content reference while maintaining a contemplative narrative about the universe and humanity's quest to understand it. In the vast tapestry of the cosmos, where galaxies spiral in silent majesty and stars burn with ancient fires, a traveler emerged from the shadows of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System at Rio Hurtado, Chile, 3I Atlas, also known as C2025N1, Atlas, is a comet unlike any other. Ampera's wanderer born among the stars, it carries secrets of a distant past etched into its icy nucleus and trailing clouds of gas and dust. As the third interstellar object confirmed to pass through our solar system, following the enigmatic 1I Oumuamua, 2017, and the more familiar 2I Borisov, 2019, 3I Atlas is a testament to the interconnectedness of the universe. Its arrival stirs curiosity and wonder, a reminder that we are not alone in the cosmic dance of matter and energy. Yet it is not merely its origin that captivates scientists and dreamers alike. It is the story it tells, a story of ancient stellar nurseries, volatile ices, and the relentless pull of gravity shaping its trajectory through the void. When the Atlas telescopes first captured the faint glimmer of 3I Atlas, it was already deep in the embrace of the inner solar system. At a distance of 4.5 astronomical units, AU, from the Sun, the comet was hurtling through space at an astonishing 58 kilometers per second, 36 miles per second, a speed far exceeding the gravitational grip of our star. Initial observations were fraught with uncertainty. Was this a rogue asteroid, a frozen relic of a distant star system, or something else entirely? The answer lay in its trajectory, a hyperbolic path that bent sharply around the Sun before escaping into the abyss. With an orbital eccentricity of 6.141, the highest of any interstellar object yet observed, 3I Atlas's journey was never meant to be a detour. It was a one-way ticket, forged by the gravitational slingshot of its home system, and now hurtling toward the edge of our cosmic neighborhood. The confirmation of 3I Atlas's interstellar origins came swiftly thanks to a global network of observatories. The Zwicky Transient Facility, ZTF, in California, and the Nordic Optical Telescope in the Canary Islands provided critical pre-discovery data, revealing that the comet had passed near the galactic center, a region teeming with stars, yet hiding 3I Atlas in plain sight. The comet's retrograde orbit, tilted 175 degrees relative to the ecliptic, further underscored its alien nature. Unlike the majority of objects in our solar system, which orbit the Sun in a relatively flat plane, 3I Atlas arrived from above the galactic plane, a trajectory that hinted at its origin in the Milky Way's thick disk, a population of older stars and interstellar material. Yet, the true marvel of 3I Atlas lies not in its speed or path, but in its composition. As it neared the Sun, telescopes across the world turned their gaze toward this visitor. The Hubble Space Telescope revealed a coma spanning thousands of kilometers, a cloud of gas and dust billowing from its nucleus. The James Webb Space Telescope, more JWST, detected an abundance of carbon dioxide, a rarity in solar system comets, suggesting that 3I Atlas formed in a frigid region far from its parent star, where CO2 could condense into ice. Meanwhile, the Very Large Telescope, more JADE, uncovered traces of cyanide and atomic nickel vapor, chemicals typically associated with the violent outgassing of comets, but rarely seen in such concentrations. Each observation added another piece to the puzzle, painting a portrait of a comet that was both familiar and alien, a bridge between the birthplaces of stars and the frozen realms of planetary systems. To understand 3I Atlas is to peer into the cradle of a distant star. Its nucleus, shrouded in a veil of gas and dust, remains an enigma. Estimates place its diameter between 0.32 and 5.6 kilometers, though the exact figure eludes scientists due to the overwhelming brightness of its coma. What is clear, however, is that 3I Atlas is a dynamic world. As sunlight strikes its surface, volatile ices, water, carbon dioxide, and carbon monoxide sublimate into gas, carrying with them fragments of rock and organic compounds. This process forms the coma, a glowing halo that expands outward, and the dust tail, a stream of particles pushed by solar radiation. The comet's activity intensifies with each passing day. By late July 2025, observations revealed a sun-facing plume of dust erupting from its nucleus, a phenomenon seen in other distant comets like C-2014 UN-271, Bernardinelli, Bernstein. This plume, stretching tens of thousands of kilometers, suggests that 3I Atlas's surface is unevenly heated, with regions of ice melting faster than others. The resulting jets of gas and dust sculpt its coma into a lopsided shape, a fleeting masterpiece of cosmic artistry. But 3I Atlas is more than a spectacle. It is a time capsule. The presence of heavy carbon isotopes in its CO2 and the absence of certain organic molecules hint at a history shaped by the unique conditions of its birthplace. If 3I Atlas indeed hails from the Milky Way's thick disk, it could be over 7 billion years old, longer than the age of our solar system. Such an age implies that the comet witnessed the early days of the galaxy, a witness to the formation of stars and the dispersal of primordial materials. Its journey through interstellar space may have taken it past the remnants of ancient supernovae, through the gravitational tides of neighboring stars, and into the quiet void between stellar systems. The implications of 3I Atlas extend beyond its own story. By studying its composition and behavior, scientists hope to unravel the mysteries of how comets form in other star systems. Are the processes that created 3I Atlas similar to those that shaped the comets of our own solar system? Or does its chemistry reflect the idiosyncrasies of its parent star, a system vastly different from ours? The answers lie in the data, but the questions themselves remind us of the vastness of the unknown. Each grain of dust in 3I Atlas's coma is a message from a distant world, a whisper carried across the interstellar gulf. Despite the wealth of knowledge gleaned from 3I Atlas, its journey through the inner solar system is a race against time. By October 2025, the comet will reach perihelion, the point of closest approach to the Sun, at a distance of 1.36 AU, nestled between the orbits of Earth and Mars. From our vantage point, however, 3I Atlas will vanish behind the Sun, cloaked in the glare of solar radiation. Only Mars orbiters may glimpse it during this critical phase, capturing data that could illuminate the final stages of its transformation. As it departs the solar system, its brightness will fade, and its dust will scatter into the void, leaving Earthbound observers with memories of a fleeting encounter. Yet, 3I Atlas's story is far from over. The lessons it imparts will echo through the halls of science for decades to come. Its discovery underscores the limitations of our current observational tools, a humbling reminder that countless interstellar visitors may pass unnoticed. The Vera C. Rubin Observatory, with its unprecedented ability to scan the skies, promises to change this. By detecting faint objects like 3I Atlas at earlier stages, it will expand our understanding of the interstellar population and their origins. Future missions, perhaps even interstellar probes, may one day follow in the footsteps of this comet, venturing into the unknown to uncover the secrets of the cosmos. As 3I Atlas fades from view, it leaves behind a question as profound as the universe itself. How many more travelers like it await discovery, drifting silently through the dark, waiting for their stories to be told? In the vast, silent expanse of the cosmos, comets are the storytellers of the stars. They are remnants of ancient worlds, born in the frozen outskirts of distant systems and cast adrift as cosmic wanderers. Among them, 3I Atlas stands apart, not merely as a transient visitor to the solar system, but as a harbinger of interstellar secrets. As it hurtles inward on a hyperbolic path, its nucleus stirs under the sun's gaze, birthing plumes of dust and gas that shimmer like ghostly breath in the void. These phenomena are not random. They are the fingerprints of a process as old as the universe itself. The transformation of ice into vapor, the dance of matter and energy that shapes the destinies of comets. To witness 3I Atlas's activity is to peer into the heart of a celestial engine, where sunlight acts as both sculptor and catalyst, carving intricate patterns into the comet's fragile form. Yet 3I Atlas is more than a passive actor in this drama. Its dust plumes and tails are dynamic, shifting in response to the sun's pull and the comet's own internal rhythms. Amper's sun-facing plume rises from its nucleus, a testament to the volatile materials that lie buried beneath its surface. Meanwhile, a tail stretches outward, defying the direction of the comet's motion, as if to declare its allegiance to the star that now warms it. These features are not unique to 3I Atlas. They echo the behavior of countless comets within our own solar system. But in the case of this interstellar traveler, they carry an added layer of intrigue. What secrets do these plumes and tails reveal about the conditions in the distant stellar neighborhood from which 3I Atlas originates? And how do they reflect the comet's ancient, undisturbed state? As we unravel these questions, we find ourselves standing at the intersection of cosmic history and present-day observation, where every grain of dust and molecule of gas holds a story waiting to be told. At the core of 3I Atlas's activity lies the sun, a fusion-powered lighthouse that bathes the comet in light and heat. When the comet's nucleus, a frozen mixture of rock, ice, and organic compounds, absorbs solar energy, the volatile ices within begin to sublimate. This process transforms solid carbon dioxide, water ice, and carbon monoxide directly into gas, bypassing the liquid phase entirely. The resulting outgassing propels dust particles from the comet's surface, creating a coma, a glowing envelope of gas and debris that surrounds the nucleus. The coma expands outward, forming a complex dynamic structure that evolves as the comet approaches the sun. One of the most striking features of 3I Atlas is its sun-facing plume, a jet of material that streams from the nucleus toward the direction of the sun. This phenomenon arises because the sun's rays strike the comet's surface unevenly, heating specific regions more intensely. Where the temperature rises sufficiently, volatile ices sublimate rapidly, generating localized bursts of gas and dust. These eruptions create a plume that extends outward from the nucleus, often appearing as a distinct elongated feature in telescope images. Unlike the comet's tail, which points away from the sun, the plume is a direct consequence of the sun's influence, a reminder that the comet's activity is driven by the very star it is approaching. As 3I Atlas continues its journey, The interaction between its coma and the solar wind gives rise to another iconic cometary feature, the tail. The tail forms when charged particles in the solar wind push ionized gas molecules away from the coma, while the sun's radiation pressure gently nudges dust particles into a separate, more diffuse stream. The result is a dual-tailed structure, one composed of ionized gases, the other of microscopic dust grains. The tail of 3I Atlas, though faint, has been observed to stretch tens of thousands of kilometers from its nucleus, a visual record of the comet's recent passage through the inner solar system. Observations by the James Webb Space Telescope, JWST, and the Hubble Space Telescope have provided critical insights into the mechanics of 3I Atlas's activity. JWST's infrared capabilities have revealed the comet's rich carbon dioxide content, identifying plumes of CO2 gas that erupt from its surface. These emissions suggest that the comet's interior is not only icy but also highly volatile, with CO2 playing a dominant role in driving outgassing. Meanwhile, Hubble's high-resolution imaging has captured the evolution of the coma's dust distribution, showing how particles of varying sizes respond to solar radiation. Smaller grains are carried farther from the nucleus, forming a broad, diffuse tail, while larger particles remain closer to the coma, contributing to its reddish hue. The dynamics of 3I Atlas's activity are further illuminated by spectroscopic analysis conducted by ground-based observatories, such as the Very Large Telescope, VLT. These studies have identified the presence of cyanide gas and atomic nickel vapor in the coma, substances commonly associated with cometary activity in the solar system. The detection of nickel is particularly intriguing, as it suggests that the comet's surface contains trace metals that are released during outgassing. The absence of iron, however, remains a mystery, hinting at differences in the comet's composition compared to solar system analogues. Such findings underscore the complexity of interstellar comets, which may carry signatures of their parent star systems in their chemical makeup. The activity of 3I Atlas offers a unique window into the conditions of the interstellar medium. The vast, diffuse expanse of gas and dust that fills the spaces between stars. As the comet traverses its hyperbolic trajectory, it carries with it the imprint of its origin, the temperature, pressure, and chemical environment of the stellar nursery where it was born. The fact that 3I Atlas remains active at such a great distance from the Sun, its current location is nearly 3 times farther from the Sun than Earth's orbit, suggests that its volatile ices are particularly sensitive to solar heating. This heightened reactivity may stem from the comet's ancient undisturbed state, preserved for billions of years in the cold depths of interstellar space. The presence of carbon dioxide as a primary driver of 3I Atlas's outgassing also raises profound questions about its formation history. In our own solar system, CO2 is typically found in comets that originate from the distant Oort cloud, where temperatures are so frigid that the gas can condense into solid form. The abundance of CO2 in 3I Atlas implies that the comet may have formed in a similarly cold environment, perhaps in the outer reaches of its parent star system. However, the comet's high CO2 to water ratio, which exceeds that of most solar system comets, hints at a different evolutionary path. One possibility is that 3I Atlas formed in a protoplanetary disk where CO2 was more prevalent, or that it underwent prolonged exposure to cosmic radiation, altering its chemical composition over time. Moreover, the comet's activity provides clues about the mechanisms that govern the dispersal of cometary material. The ejection of dust and gas from 3I Atlas's nucleus is not uniform. Instead, it occurs in discrete jets and plumes, suggesting that the comet's surface is heterogeneous. Some regions may be rich in volatile ices, while others are barren or coated in a layer of refractory material. This variability mirrors what is observed in solar system comets, where surface features such as cliffs, pits, and fissures serve as conduits for outgassing. The fact that 3I Atlas exhibits similar behavior despite its interstellar origins underscores the universality of cometary processes, reinforcing the idea that the fundamental physics governing these objects is consistent across the cosmos. Perhaps the most tantalizing implication of 3I Atlas's activity is its potential to shed light on the formation and evolution of planetary systems. By studying the comet's composition and behavior, astronomers can infer the conditions under which it formed, offering indirect insights into the environments of its parent star system. For instance, the detection of amorphous water ice in the Coma suggests that the comet's surface has not undergone significant thermal processing, preserving the primordial state of its materials. Similarly, the presence of heavy carbon isotopes in CO₂ molecules may provide information about the stellar processes that contributed to the comet's creation. These findings contribute to a growing body of knowledge about the diversity of planetary systems in the Milky Way, highlighting the ways in which different stars and their accompanying disks give rise to unique populations of small bodies. As 3I Atlas continues its journey through the inner solar system, its activity reveals not only the nature of its own composition, but also the forces that shape comets across the universe. Yet, beneath the surface of this dynamic display lies another enigma: the rotation of its nucleus. Unlike the predictable spin of planets, the comet's rotation is erratic, influenced by the uneven release of gas and dust that alters its angular momentum. This instability raises questions about the comet's internal structure and the mechanisms that govern its motion. Is 3I Atlas a single cohesive body, or is it a loosely bound aggregate of fragments held together by gravity? Could its rotation be a consequence of past collisions or gravitational interactions with other objects in its home system? These questions beckon us forward, inviting a deeper exploration of the comet's physical characteristics and the cosmic forces that define its fate. In the next segment, we turn our gaze to the nucleus of 3I Atlas, where the answers to these mysteries may lie hidden beneath layers of ice and dust. In the vast, silent expanse of the universe, where galaxies spiral like whirlpools of stardust and planets drift through the void, a solitary traveler emerged from the darkness. 3I Atlas, a comet born in the icy depths of another star system, arrived in our solar neighborhood on 1 July 2025. Discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS, at Rio Hurtado, Chile. This interstellar wanderer carried with it secrets of distant worlds and ancient histories. Its arrival marked a rare cosmic event, the third confirmed visitor from beyond our solar system, following the enigmatic 1I Oumuamua in 2017 and the mysterious 2I Borisov in 2019. Yet, unlike its predecessors, 3I Atlas did not merely pass through. It danced with the sun, shedding light on its origins and the processes that shape comets across the galaxy. The comet's journey began in the cold, dark realms of interstellar space, where it traveled at a blistering 58 kilometers per second, a velocity so great that it could not be captured by the sun's gravity. Instead, it followed a hyperbolic path, a cosmic slingshot that would carry it back into the interstellar abyss. From its discovery at 4.5 astronomical units, AU, from the Sun to its closest approach, on 29 October 2025, 3I Atlas offered humanity a fleeting glimpse into the mechanics of a world born in another stellar cradle. Its trajectory, aligned almost retrograde with the ecliptic plane, hinted at a violent ejection from its parent system, perhaps by the gravitational pull of a giant planet or a passing star. Yet, 3I Atlas was more than a mere interloper. Its Coma, a swirling halo of gas and dust, revealed a chemical fingerprint unlike any seen in our own solar system. Rich in carbon dioxide, water ice, and exotic molecules like carbonyl sulfide, the comet carried echoes of its birthplace. As it approached the Sun, its nucleus began to warm, triggering sublimation of ices and the release of volatile compounds. Each molecule escaped into space, forming a luminous envelope that shimmered in the light of distant stars. To observers on Earth, it was a quiet symphony of cosmic transformation, a reminder that even the smallest specks of matter hold stories spanning billions of years. What then does 3I Atlas teach us? As it hurtled toward its perihelion, its presence stirred questions about the universality of comet formation, the dynamics of interstellar travel, and the fragile connection between stars. Could it have originated from the thick disk of the Milky Way, a population of ancient stars older than our solar system? Was its parent star a metal-poor giant? Its protoplanetary disk a crucible of carbon-rich compounds? And what might its eventual fate be, as it escaped the sun's grasp, carrying with it the imprints of a civilization of ice and rock that would never return? These mysteries, suspended in the delicate balance between science and wonder, invite us to ponder our place in the grand tapestry of the cosmos. At its heart, 3I Atlas is a relic of cosmic alchemy. Its nucleus, a frozen core of rock, ice and organic compounds, is the remnant of a protoplanetary disk that once swirled around a long-vanished star. Though shrouded in a haze of gas and dust, the nucleus itself is estimated to be less than 1 kilometer in diameter, a modest size compared to the titanic planets of our solar system, yet sufficient to unleash a storm of activity as it nears the Sun. Observations by the Hubble Space Telescope and the James Webb Space Telescope, JWST, revealed a coma stretching tens of thousands of kilometers, its glow a testament to the comet's internal volatility. The Sun, a relentless force of energy, plays a central role in awakening 3I Atlas. As the comet's orbit brought it closer to our star, solar radiation penetrated its icy exterior, heating volatile materials and triggering a cascade of sublimation. Carbon dioxide, water ice, and carbon monoxide transformed from solid to gas, erupting in jets that lifted dust particles into the coma. These particles, ranging from micrometers to millimeters in size, scattered sunlight, creating a diffuse reddish glow. The coma's composition, dominated by CO₂ and trace amounts of water vapor, set 3I Atlas apart from typical solar system comets, which often exhibit higher proportions of water and methane. This discrepancy hinted at a formation environment far colder than our own, perhaps beyond the CO₂ frost line, where temperatures are low enough for the gas to freeze into solid. The comet's tail, a defining feature of cometary activity, emerged as a faint anti-solar plume. Unlike the dramatic, sweeping tails of famous comets like Halley's or Hale-Bopp, 3I Atlas's tail was subtle, its structure dictated by the balance between solar radiation pressure and the comet's own momentum. Small dust grains, accelerated by sunlight, trailed behind the nucleus in a broad feathery arc, while larger particles lingered closer to the coma. This duality reflected the comet's internal dynamics: rapid, chaotic outflows from its sunlit hemisphere, and slower, more uniform emission from its darker side. The tail's evolution, observed by the Gemini South Telescope, grew from 30 arcseconds in July to over 56,000 kilometers by August, a silent testament to the comet's increasing activity. Beneath this surface spectacle lay a more intricate dance of molecules. The JWST's infrared spectrometers detected a wealth of volatile compounds, including carbon monoxide, carbonyl sulfide, and the elusive isotope carbon-13 in CO₂. These molecules, forged in the frigid depths of interstellar space, offered clues about the comet's history. The presence of heavy isotopes suggested prolonged exposure to cosmic rays, while the absence of certain carbon chain compounds, such as dicarbon, Mihal C2 and tricarbon, C3, indicated a chemical profile distinct from that of native solar system comets. The Very Large Telescope, VLT, further enriched this picture, detecting cyanide gas and atomic nickel vapor in the coma. These elements, typically associated with the breakdown of organic materials, hinted at a complex, irradiated surface. Yet 3I Atlas's most striking feature was its abundance of carbon dioxide, with a mixing ratio of CO₂ to water 8 times higher than typical comets. The comet defied expectations. Did this reflect a CO₂-rich nucleus, or was its water locked beneath an insulating crust? The answer remained elusive, but the implications were profound. If 3I Atlas had formed near the CO₂ frost line of its parent system, it could have originated in a disk with conditions vastly different from our own. Alternatively, its high CO₂ content might stem from prolonged exposure to interstellar radiation, altering the chemistry of its ices over billions of years. Either way, the comet served as a cosmic Rosetta Stone, offering insights into the diversity of planetary systems and the processes that govern their evolution. Even the comet's rotation told a story. Observations by Hubble and ground-based telescopes revealed a nucleus spinning every 16.79 hours, its irregular shape causing subtle fluctuations in brightness. The rotation axis, however, was obscured by the expanding Coma, making precise measurements challenging. This instability raised intriguing questions. Would 3I Atlas fragment under the stress of its spin, as 2I Borisov had, or would its nucleus endure, a resilient survivor of countless interstellar journeys? The answers, hidden in the comet's final days, awaited further scrutiny. Through these layers of complexity, 3I Atlas emerged as more than a transient visitor. It was a laboratory of cosmic chemistry, a chronicle of stellar nurseries, and a mirror reflecting the conditions of a universe in constant flux. Its passage through the solar system was a fleeting moment, yet within it lay the echoes of epochs past and the promise of discoveries yet to come. To unravel the origins of 3I Atlas is to embark on a voyage through time and space, tracing its path from the distant reaches of the galaxy to the fleeting warmth of our solar system. The comet's hyperbolic trajectory, defined by an orbital eccentricity of 6.14, places it among the most extreme interstellar visitors ever recorded. Unlike 1I Oumuamua and 2I Borisov, which originated from the galactic disk near the Sun's position, 3I Atlas hailed from the southern celestial hemisphere, a region opposite the solar apex, the direction of the Sun's motion relative to nearby stars. This southern provenance was unexpected. Astronomers had anticipated that interstellar objects would arrive primarily from the solar apex, where the density of stellar encounters is higher. The discovery of 3I Atlas challenged this assumption, suggesting that southern origin comets may be more common than previously thought, or that our observational biases have limited our understanding of the galactic distribution of such objects. The comet's velocity components offer further clues. Moving at 58 kilometers per second, relative to the Sun, 3I Atlas possessed a vertical component of 18.5 kilometers per second, tilting its orbit at 5 draught to the galactic plane. This dynamic signature aligns it with the thick disk population of the Milky Way, a collection of ancient stars with low metallicity and a history of minimal interaction with the galactic center. The thick disk, a relic of the galaxy's early formation, is home to stars older than 7 billion years, far exceeding the age of our solar system, 4.6 billion years. Studies by Matthew Hopkins and Asta Taylor independently estimated 3I Atlas's age at 7.614 billion years, placing it in the twilight of cosmic history. Such an antiquity implies that the comet predates the Sun's birth, surviving eons of interstellar travel through collisions, radiation, and the gravitational tides of stars. If 3I Atlas indeed hails from the thick disk, its parent star was likely a metal-poor giant, a relic of the galaxy's formative years. Protoplanetary disks around such stars would have been rich in carbon-bearing ices, favoring the formation of CO₂-dominated bodies like 3I Atlas. Yet the comet's journey has not been passive. Over billions of years, it has likely encountered dozens of stars, each interaction nudging its trajectory. AMPA's study by Ying Guo identified 25 such encounters within 1 parsec, 3.3 light-years in the past 10 million years, a testament to the chaotic dance of stellar neighbors in the Milky Way. These close calls may have stripped 3I Atlas of its outer layers, exposing deeper, pristine material, or conversely, may have infused it with new chemical signatures from neighboring systems. The implications of these findings extend beyond 3I Atlas itself. Its composition, particularly its high CO₂ content, challenges models of comet formation in the solar system. In our own planetary nursery, comets formed beyond the water and methane frost lines, but their CO₂ levels are typically lower. The presence of CO₂ in such abundance suggests that 3I Atlas originated in a disk with a different thermal and chemical equilibrium, one where CO₂ could dominate over water. This raises profound questions. Are such CO₂-rich comets common in other systems? Do they serve as reservoirs for carbon-based life? Or do they represent a unique chapter in the history of their parent star's birthplace? Yet the quest to understand 3I Atlas is fraught with challenges. Its trajectory, while revealing, is ultimately a puzzle, without a complete picture. The parent star that birthed it remains unknown, lost to the eons of galactic migration. Attempts to trace its origin via stellar kinematics have yielded no definitive matches, leaving astronomers to rely on indirect inferences. Meanwhile, the comet's chemical profile, though rich in data, is incomplete. The absence of certain molecules, like carbon chain compounds, and the delayed detection of water vapor hint at a complex evolutionary history. Perhaps 3I Atlas's ices have been shielded by a thick crust, or its surface has been altered by prolonged exposure to cosmic rays. Without a sample return mission, which remains beyond current technological capabilities, the comet's secrets will remain tantalizingly out of reach. These uncertainties, however, are not barriers but invitations to explore. The James Webb Space Telescope and ground-based observatories continue to monitor 3I Atlas as it retreats from the Sun, their instruments capturing spectral fingerprints that may refine our understanding of its composition. Simulations of its trajectory and interactions with the solar system's planets offer glimpses into the mechanics of interstellar travel, while comparisons with 2I Borisov and 1I Oumuamua illuminate patterns in the behavior of such objects. Even the controversy surrounding Avi Loeb's hypothesis that 3I Atlas could be an alien spacecraft has spurred debate, reminding us that the boundaries between the known and the unknowable are as fluid as the comets themselves. Ultimately, 3I Atlas is a bridge between worlds. It carries the legacy of a star that no longer shines, the chemistry of a protoplanetary disk long dissipated, and the resilience of a body that has endured the vast, indifferent expanse of interstellar space. Its story is not merely one of a comet's passage through our solar system, but of the interconnectedness of all things in the universe, a reminder that the cosmos is a tapestry woven from the threads of countless histories, each waiting to be unraveled. As 3I Atlas recedes from the Sun, its brilliance fades into the cosmic night, a silent testament to the impermanence of all things. By November 2025, its solar elongation will stretch to 30 degrees, allowing observers on Earth to glimpse it once more, though only briefly, as its coma dims and its tail dissolves into the void. The James Webb Space Telescope and Hubble will continue their vigil, tracking the comet's escape from the solar system and analyzing the final whispers of its gas emissions. Yet even these instruments will eventually lose sight of 3I Atlas, its trajectory bending back toward the interstellar abyss from which it came. Its departure marks not an end, but a beginning. The data gathered during its brief visit will fuel decades of study, refining models of cometary formation, interstellar dynamics, and the chemical diversity of planetary systems. Already, the comet's CO₂-rich Coma has reshaped our understanding of the conditions under which such bodies can form. Its southern origin has challenged assumptions about the distribution of interstellar objects in the galaxy, while its age, potentially older than the solar system, has opened new avenues for exploring the evolution of the Milky Way. Even the controversies surrounding its nature, from the debate over its parent star to the speculative theories of its artificiality, underscore the humility required in the face of the unknown. And yet, 3I Atlas is but one of many. In the coming centuries, as surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, scan the skies with unprecedented precision, we may discover hundreds of interstellar visitors, each a messenger from a distant corner of the galaxy, each a fragment of a story we have yet to tell. These objects, like 3I Atlas, will challenge our preconceptions, expand our horizons, and remind us that the universe is not a static expanse, but a living, evolving entity. In the end, the comet's journey is a parable for our own. Just as 3I Atlas traverses the void, carrying the imprint of its origin, so too do we navigate the vastness of existence, seeking meaning in the fleeting moments of connection. Its passage through the solar system is a reminder that we are not alone in the cosmos, not as individuals, nor as a species, but part of a grand, interconnected web of matter and energy, forever reaching outward in search of understanding. In the vast tapestry of the cosmos, where galaxies swirl and stars are born, one object has captured the imagination of humanity: 3I Atlas, the third interstellar comet ever discovered. First glimpsed on 1 July 2025 by the Atlas telescope in Chile, this enigmatic traveler arrived in our solar system as a silent witness to the ancient history of the Milky Way. Its arrival is not merely a scientific curiosity, but a profound reminder of our place in the universe, a fleeting intersection of paths, where a relic of another stellar neighborhood brushes against our own. 3I Atlas enters the inner solar system at a staggering speed of 58 kilometers per second, hurtling along a hyperbolic trajectory that defies the gravitational pull of the Sun. Unlike the countless asteroids and comets that originate within our solar system, 3I Atlas is a stranger, born in the cold depths of interstellar space, and now passing through our cosmic backyard. Its journey spans billions of years, and its story is etched in the frozen chemistry of its nucleus and the shimmering coma that trails behind it. To observe this comet is to peer into the distant past, to witness the remnants of a star system long vanished, carried forward by the inexorable motion of the galaxy. What makes 3I Atlas particularly remarkable is not just its origin, but the wealth of information it brings. As it approaches the Sun, its icy heart begins to awaken, releasing jets of gas and dust that reveal clues about its composition. Carbon dioxide, water ice, and traces of cyanide and nickel vapor tell a tale of a world shaped by the crucible of another solar system. Yet, for all its revelations, 3I Atlas remains an enigma. How did it form so far from its parent star? What secrets lie buried in its nucleus? And what does its existence say about the interconnectedness of the cosmos? These questions echo in the minds of scientists and dreamers alike, drawing us deeper into the mystery of this interstellar visitor. As 3I Atlas continues its path, it serves as a bridge between worlds, a testament to the dynamic, ever-changing nature of the universe. Its story is not just one of science, but of wonder, inviting us to gaze upward and ponder the infinite expanse beyond our own solar system. The discovery of 3I Atlas was a triumph of modern astronomy, a moment where technology and human ingenuity converged to unveil a cosmic secret. On that fateful night in July 2025, the Atlas telescope at Rio Hurtado, Chile, captured the first glimpse of a faint, moving object against the backdrop of the Milky Way. Initially catalogued as a 11 Pli 3Z, the object's trajectory quickly raised eyebrows. Its velocity, 61 kilometers per second, relative to the Sun, was far too great to be explained by the gravitational dance of our solar system alone. Follow-up observations by the Zwicky Transient Facility and the Very Large Telescope confirmed what seemed impossible. 3I Atlas was on a hyperbolic path, destined to escape the Sun's grasp entirely. What followed was a flurry of scientific inquiry. Astronomers scrambled to classify the object, unsure whether it was a comet or an asteroid. Early images showed a faint glow, but it was the detection of a coma, a cloud of gas and dust, by the Deep Random Survey and the Lowell Discovery Telescope that settled the question. By 2 July 2025, the Minor Planet Center officially designated the object a C₂-Rich 2025 N1 not class, AT class, recognizing it as the third interstellar object to ever be observed. The name 3I AT class was bestowed upon it, a prefix denoting its interstellar heritage and a tribute to the telescope that first spotted it. The true nature of 3I Atlas began to emerge as powerful instruments turned their gaze toward the comet. The Hubble Space Telescope, with its unparalleled resolution, revealed the structure of the coma and placed constraints on the size of the nucleus, estimating it to be less than 1 kilometer in diameter. Meanwhile, the James Webb Space Telescope, JWST, probed deeper, detecting a treasure trove of volatile compounds. Carbon dioxide dominated the coma, far richer than in most solar system comets, alongside water ice, carbon monoxide, and carbonyl sulfide. The Very Large Telescope added to the mosaic of discovery, identifying cyanide gas and atomic nickel vapor, chemical fingerprints of a body forged in the cold, distant reaches of interstellar space. Even as 3I Atlas approached the Sun, Its behavior defied expectations. Unlike typical comets which brighten dramatically as they near perihelion, 3I Atlas exhibited a steady, measured increase in activity. Observations by NASA's Transiting Exoplanet Survey satellite, TESS, showed that the comet had already begun sublimating its ices as early as May 2025, when it was 6.4 astronomical units AU from the Sun. This hinted at an unusual composition, one where carbon dioxide and other volatile ices played a more prominent role than water. The comet's dust coma, spanning tens of thousands of kilometers, was another anomaly. High-resolution images from the Gran Telescopio Canarias revealed a complex structure, with a sun-facing plume of ejected material and a faint anti-solar tail. The trajectory of 3I Atlas told a story of its own. With an orbital eccentricity of 6.141, its path was nearly straight, a stark contrast to the elliptical orbits of native solar system bodies. This extreme eccentricity meant that 3I Atlas's approach to the Sun was brief and swift. On 29 October 2025, it would reach perihelion at a distance of 1.36 AU, nestled between the orbits of Earth and Mars. Yet, despite its proximity to the inner solar system, the comet posed no threat to Earth, remaining safely at a distance of over 1.8 AU at its closest approach. As the comet's journey unfolded, so too did the story of its origin. By analyzing its velocity vector, astronomers deduced that 3I Atlas hailed from the southern celestial hemisphere, a direction opposite to the Sun's motion through the galaxy. This was a surprise, as earlier models predicted that most interstellar objects would arrive from the solar apex. The comet's high vertical velocity component, moving upward through the galactic plane, suggested it belonged to the Milky Way's thick disk, a population of older stars with lower metallicity. If 3I Atlas indeed originated from this ancient stellar neighborhood, it could be over 7 billion years old, predating the formation of our solar system. Each observation brought new layers of understanding, yet mysteries persisted. Why did the comet's coma contain such an abundance of carbon dioxide? What mechanisms governed its dust ejection? And how could it maintain such a stable activity profile without sudden outbursts or fragmentation? These questions lingered as scientists prepared for the next phase of exploration. The discovery of 3I Atlas has reshaped our understanding of the cosmos, offering a rare glimpse into the chemistry and dynamics of interstellar objects. Unlike the first two interstellar visitors, 1I Oumuamua and 2I Borisov, 3I Atlas stands apart due to its prolonged activity and the wealth of data collected about its composition. While Oumuamua remained an enigmatic asteroid-like object, with no detectable coma, and Borisov displayed familiar comet-like traits, 3I Atlas unveiled a unique blend of characteristics. Its high carbon dioxide content, for instance, challenges existing models of cometary formation, suggesting that it may have originated in a protoplanetary disk, where CO₂ ice was abundant. This raises intriguing questions about the diversity of planetary systems across the galaxy and the conditions under which such volatile rich bodies can form. Perhaps most astonishing is the age of 3I Atlas. If it indeed hails from the Milky Way's thick disk, the comet could be over 7 billion years old, a relic from a time when the galaxy itself was young. This would place its formation in an era before the Sun's birth, making it a cosmic fossil carrying the imprint of an ancient stellar nursery. Such an object offers a direct window into the early Milky Way, allowing scientists to study the chemical evolution of the galaxy through its composition. The presence of heavy elements like nickel and cyanide in its coma, for example, hints at the influence of supernovae and stellar winds in shaping its parent system. These findings underscore the interconnectedness of the galaxy, where the life cycles of stars and the dispersal of their remnants create a shared cosmic heritage. Yet the story of 3I Atlas is not without controversy. In July 2025, astrophysicist Avi Loeb proposed a radical hypothesis that the comet might be an alien spacecraft, citing its trajectory alignment with the ecliptic plane and its apparent lack of certain identifiable chemicals. Loeb argued that 3I Atlas could harbor artificial origins. This speculation ignited fierce debate within the scientific community. Critics quickly pointed out that the comet's trajectory, while unusual, was not impossible for a natural object, and that the absence of certain compounds could simply reflect observational limitations. Furthermore, subsequent observations by the James Webb Space Telescope and the Very Large Telescope confirmed the presence of carbon dioxide, water, and cyanide chemicals commonly found in comets. The Swift Observatory even detected water vapor and hydroxyl radicals, reinforcing the conclusion that 3I Atlas is a natural body, despite the swift refutation of Loeb's hypothesis. The episode highlighted the delicate balance between scientific rigor and open-minded speculation. While the burden of proof for extraordinary claims remains high, the discussion underscored the importance of considering all possibilities, however unlikely. After all, the very existence of interstellar objects like 3I Atlas was once deemed improbable, yet here it was, traversing our solar system as a testament to the universe's boundless surprises. The legacy of 3I Atlas extends beyond its scientific value. It has inspired a renewed focus on interstellar object detection and interception, prompting discussions about future missions to study such visitors up close. While launching a probe to 3I Atlas proved impractical due to its rapid departure, the comet's trajectory has informed strategies for intercepting future interstellar comets. Concepts for missions equipped with advanced propulsion systems, such as solar sails or nuclear thermal engines, are already in development, aiming to reach these elusive targets before they vanish into the void. Moreover, 3I Atlas has deepened our appreciation for the transient beauty of the cosmos. Its journey through the solar system, marked by the quiet release of gas and dust, serves as a reminder of the impermanence of celestial phenomena. Yet, even as it fades from view, the data it leaves behind will endure, fueling generations of research and inspiring new questions about the nature of our galaxy and the origins of life itself. As 3I Atlas continues its flight beyond the solar system, it carries with it the hopes and questions of humanity. Its departure marks not an end but a beginning, a call to refine our tools, expand our horizons, and prepare for the next interstellar visitor. Already, astronomers are training their eyes on the skies, eager to catch the next glimpse of a rogue comet or asteroid that might one day cross our path. What lies ahead is a future where interstellar exploration is no longer a dream, but a tangible goal. Missions like the Vera C. Rubin Observatory and the upcoming Interstellar Object Interceptor (IOI) project promise to revolutionize our ability to detect and study these cosmic wanderers. Perhaps one day, a spacecraft will rendezvous with an interstellar comet, unraveling its secrets in real time. Until then, 3I Atlas remains a symbol of the universe's vastness and our unyielding curiosity, a reminder that the answers we seek are often found in the most unexpected places. And so, as we turn our gaze skyward, we do so with the knowledge that we are not alone in the cosmos. We are part of a grand unfolding story, one where every star, every planet, and every passing comet whispers the truth of our shared existence. In the quiet journey of 3I Atlas, we find not only the echoes of a distant past, but the promise of a future yet to be written. In the vast expanse of the cosmos, where stars twinkle like distant sentinels and galaxies spiral in silent grandeur, a new interloper has emerged, a comet born not in the familiar confines of the solar system, but from the uncharted reaches of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, station in Chile, 3I Atlas, also known as C2025N1, ATLAS, marks itself as the third confirmed interstellar object to traverse our celestial neighborhood. Its arrival is a reminder of the dynamic nature of the universe, where the boundaries between systems blur and the dance of matter across the void defies the notion of isolation. 3I Atlas is no ordinary traveler. It hurtles through the solar system on a hyperbolic trajectory, unbound by the sun's gravitational embrace. With a velocity of 58 kilometers per second, more than double the speed of the previous interstellar visitors, 1I Oumuamua and 2I Borisov. Its path, a straight line through the cosmos, is a testament to its origins far beyond our stellar backyard. While it poses no threat to Earth, its mere presence stirs profound questions about the origins of comets, the processes of planetary formation, and the interconnectedness of stars and systems across the galaxy. What sets 3I Atlas apart is not merely its velocity or trajectory, but the wealth of mysteries it carries. Unlike the enigmatic 1I Oumuamua, which offered little in the way of clues, and the more familiar 2I Borisov, which bore the hallmarks of a typical comet, 3I Atlas reveals a complex and intriguing composition. Observations by the James Webb Space Telescope have unveiled an unusually rich mix of carbon dioxide, water ice, and other volatile compounds, hinting at a history shaped by the frigid depths of interstellar space. Its Coma, a glowing halo of gas and dust, tells a story of sublimation and outgassing, as the sun's warmth awakens the dormant materials within its nucleus. As 3I Atlas approaches its closest point to the sun on 29 October 2025, it becomes a fleeting yet profound opportunity for astronomers and dreamers alike. To witness such an object is to glimpse the raw material of worlds, the echoes of a star system long vanished, and the vast uncharted tapestry of the cosmos. In its journey, 3I Atlas embodies the spirit of exploration, a cosmic messenger reminding us that we are part of something far greater than ourselves, and that the universe is alive with stories waiting to be told. The discovery of 3I Atlas began with the vigilant gaze of the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of telescopes designed to detect potentially hazardous near-Earth objects. On 1 July 2025, ATLAS captured the first glimpse of this interstellar wanderer as it entered the inner solar system at a distance of 4.5 astronomical units, AU, from the Sun. At that moment, 3I Atlas was already moving at a staggering 61 kilometers per second relative to Earth, a speed that immediately set it apart from the usual population of asteroids and comets. Initial observations suggested a highly eccentric trajectory, prompting astronomers to submit the discovery to the International Astronomical Union's Minor Planet Center, MPC, for confirmation. However, it quickly became evident that this was no ordinary solar system object. It was on a hyperbolic path, destined to escape the sun's gravitational pull and return to the interstellar void. As follow-up observations from observatories around the world poured in, the true nature of 3I Atlas began to take shape. The Zwicky Transient Facility, ZTF, and other surveys uncovered pre-discovery data that extended back to late May 2025, revealing that the comet had passed undetected in the dense star fields near the galactic center. This region, teeming with stars and obscured by interstellar dust, posed a significant challenge for early detection. Yet, with the help of both professional and amateur astronomers, the comet's path was reconstructed, confirming its interstellar origin. By 2 July 2025, the MPC officially classified 3I Atlas as an interstellar object and assigned it the designation 3I, marking it as the third such visitor to be identified in human history. What remained uncertain at first was whether 3I Atlas was a comet or an asteroid. Its rapid movement across the sky and lack of a visible coma led some astronomers to question its classification. However, subsequent observations by the Deep Random Survey, X09, the Lowell Discovery Telescope, G37, and the Canada-France-Hawaii Telescope, T14, revealed a diffuse elongated structure, a telltale sign of cometary activity. By the end of July 2025, the evidence was clear. 3I Atlas was indeed a comet, actively shedding gas and dust as it approached the sun. The comet's coma, illuminated by sunlight, displayed a reddish hue similar to that of 2I Borisov, further supporting its identity as an interstellar traveler. With its status confirmed, attention turned to understanding the comet's physical characteristic. Early estimates of its nucleus size ranged widely, from a few hundred meters to several kilometers in diameter, due to the difficulty in separating the nucleus's light from the surrounding coma. High-resolution imaging by the Hubble Space Telescope later narrowed the estimate to between 0.32 and 5.6 kilometers, suggesting a relatively modest-sized nucleus. Meanwhile, Spectroscopic observations by the James Webb Space Telescope, JWST, and the FEREX mission revealed an unusual composition, dominated by carbon dioxide with traces of water ice, carbon monoxide, and carbonyl sulfide. These findings hinted at a formation history distinct from typical solar system comets, offering tantalizing clues about the conditions in its parent star system. As the weeks progressed, more data continued to pour in, painting a clearer picture of 3I Atlas's journey through the solar system. The comet's trajectory, defined by its extreme hyperbolic eccentricity of 6.141, placed it on a direct course toward the inner solar system, where it would reach perihelion, the closest point to the Sun, on 29 October 2025. Its path would bring it within 0.19 AU of Mars in late September, offering a rare opportunity for planetary missions to observe it from a vantage point closer than Earth. Yet despite its proximity to the inner planets, 3I Atlas would never pose a threat to Earth, its closest approach remaining at a safe distance of 1.8 AU. Each new observation deepened the mystery of 3I Atlas, fueling scientific curiosity and public fascination. Was it a fragment of a distant planetary system, Amper's relic from the early days of the Milky Way, or perhaps something even more extraordinary? As astronomers prepared for its closest approach, the comet stood as a symbol of the universe's boundless secrets, inviting us to look beyond our own solar system and consider the vast interconnected nature of the cosmos. At the heart of 3I Atlas's journey lies its extraordinary trajectory, a hyperbolic path that defies the gravitational constraints of the solar system. Unlike the elliptical orbits of planets and typical comets, which loop around the Sun in predictable cycles, 3I Atlas's trajectory is a straight line, shaped by its immense speed and the Sun's inability to bind it. The comet's hyperbolic excess velocity, measured at 58 kilometers per second, is a staggering figure, surpassing the velocities of its predecessors, 1I Oumuamua, 26 kilometers per second, and 2I Borisov, 32 kilometers per second. This velocity is not merely a number, it is a testament to the comet's origin, born from a distant star system where it was ejected into the interstellar void. The mathematical description of 3I Atlas's path is defined by its orbital eccentricity, a dimensionless parameter that quantifies the deviation of an orbit from a perfect circle. With an eccentricity of 6.14 on, 3I Atlas holds the record among confirmed interstellar objects for the most extreme trajectory. This value places the comet's path nearly straight, with only a subtle curvature as it interacts with the Sun's gravity. Such a trajectory is rare in the solar system, where most objects are bound to the Sun's gravitational field, their paths bending in elegant ellipses. 3I Atlas, however, is a free agent, a traveler unshackled by the gravitational ties that govern the motions of planets and asteroids. The comet's closest approach to the Sun, or perihelion, occurs on 29 October 2025, at a distance of 1.36 AU, between the orbits of Earth and Mars. At this point, 3I Atlas will be moving at its maximum velocity of 68 kilometers per second relative to the Sun, a speed that will propel it back into the interstellar void after its brief encounter with the inner solar system. Despite its proximity to the Sun, the comet will not come close enough to Earth, its closest approach remaining at a safe 1.8 AU. Instead, 3I Atlas will pass within striking distance of Mars, coming as close as 0.19 AU on 3 October 2025. This near miss offers a unique opportunity for planetary missions to observe the comet from a vantage point that is both closer and more favorable than Earth-based telescopes. The orientation of 3I Atlas's trajectory relative to the solar system's ecliptic plane adds another layer of intrigue. The comet's path is tilted 175 degrees from the ecliptic, placing it in a retrograde orbit that is inclined by 5 degrees. This alignment brings 3I Atlas into close proximity with Venus, Mars, and Jupiter. Though it avoids any significant interactions with these planets, the retrograde nature of its orbit is particularly noteworthy, as it suggests that 3I Atlas's origin is not aligned with the typical prograde motion of objects in the solar system. Instead, it may have been ejected from a system where orbital dynamics differ from our own. or it could have been influenced by gravitational perturbations from nearby stars or other celestial bodies. Despite its dramatic trajectory, 3I Atlas remains a faint object, its brightness limited to an apparent magnitude of approximately 11.5 at peak. This faintness presents a challenge for observers, as the comet is not visible to the naked eye and requires specialized equipment to study. From Earth, 3I Atlas is best observed using telescopes with apertures of at least 3 to 4.5 inches, a requirement that excludes casual observers, but opens the door for dedicated amateur and professional astronomers. As of September 2025, the comet's total magnitude, combining the light of its nucleus and coma, is 15.5, making it about 100 times fainter than the comet CEAS 2025 A6. Lemon. The visibility of 3I Atlas varies significantly over the months, leading up to and following its perihelion. From July to September 2025, the comet is observable after sunset, moving through the constellations of Sagittarius, Ophiuchus, Scorpius, and Libra. During this period, its brightness increases from magnitude 17.5 to 11.7, a transformation that reflects the growing activity of its nucleus as it responds to the sun's heating. However, the comet's location in the densely populated starfields near the galactic center complicates observations, as its light often overlaps with background stars. This overlap necessitates careful image processing to distinguish the comet from its stellar neighbors. By October 2025, 3I Atlas's solar elongation, the angular separation between the comet and the sun in the sky, decreases, narrowing its visibility to equatorial regions just after sunset. The comet enters solar conjunction during its perihelion, appearing behind the sun from Earth's perspective and rendering it invisible for a brief period. This conjunction is not a drawback for all observers, however. Mars orbiters, positioned on the opposite side of the Sun, may capture views of the comet as it passes within 0.19 AU of the red planet. From Earth, the comet reappears in November 2025, visible just before sunrise, and continues to dim as it recedes from the Sun. By December 2025, 3I Atlas will have moved into the constellations of Virgo and Leo, its brightness fading to below magnitude 12. The transient nature of 3I Atlas's observability underscores the urgency of scientific efforts to study the comet. Each observation contributes to a growing dataset that illuminates the comet's physical and chemical properties, providing insights into its origins and evolution. As telescopes on Earth and in space track the comet's progress, they piece together a narrative that spans billions of years, connecting the comet to the distant star system from which it came. The interstellar origin of 3I Atlas is not merely a matter of its trajectory, it is a clue to its age and the environment in which it formed. By tracing the comet's path backward through the cosmos, astronomers have determined that it originated from the direction of the constellation Sagittarius, near the Milky Way's galactic center. This location is significant, as it suggests that 3I Atlas may have formed in a region of the galaxy that is rich in star-forming activity. However, its trajectory and velocity components indicate that it does not belong to the galactic thin disk, the younger, denser population of stars that includes the Sun. Instead, 3I Atlas is a member of the thick disk, a component of the Milky Way composed of older stars with lower metallicities. The thick disk's older stellar population implies that 3I Atlas could be at least 7 billion years old, far older than the solar system, which is 4.6 billion years. This age estimate is based on the typical lifetimes of stars in the thick disk, which are longer than those in the thin disk. Ampere's study, led by Matthew Hopkins and colleagues in July 2025, placed the comet's age between 7.6 and 14 billion years with 68% confidence, a range that includes the possibility that 3I Atlas predates the formation of the solar system. An independent analysis by Asta Taylor and Daryl Seligman corroborated this finding, estimating the comet's age at 3 to 11 billion years. These figures are not mere numbers. They represent a cosmic timescale that stretches beyond the history of our own solar system, linking 3I Atlas to an era when the Milky Way was young and its star-forming regions were more active. The age of 3I Atlas raises profound questions about its formation and the conditions under which it was created. If the comet is indeed older than the solar system, It may have formed in a different galactic environment, perhaps in a region of the Milky Way that has since evolved or been disrupted by supernova explosions or gravitational interactions. Its composition, rich in carbon dioxide and other volatile compounds, hints at a formation process that occurred in the outer reaches of its parent star system, beyond the CO₂ frost line, where temperatures are low enough for the gas to condense into ice. The presence of water ice and other volatiles suggests that 3I Atlas's parent system was capable of producing cometary material, similar to that found in the solar system, albeit under different conditions. The comet's parent star remains unknown, as 3I Atlas has traveled through the Milky Way for billions of years, its path likely altered by gravitational encounters with other stars and interstellar clouds. AMPER's study by Yang Guo and collaborators in September 2025 found that 3I Atlas may have passed within 1 parsec, 3.3 light-years, of 25 known stars in the past 10 million years, suggesting that its trajectory has been subtly influenced by the gravitational forces of its galactic neighborhood. These interactions may have modified the comet's speed and direction, adding complexity to its journey through interstellar space. The thick disk's lower metallicity, its reduced abundance of elements, heavier than helium, provides additional context for 3I Atlas's formation. If the comet's parent star was a low metallicity star, its protoplanetary disk would have contained fewer heavy elements, shaping the composition of the cometary material that eventually coalesced into 3I Atlas. The comet's unusual richness in carbon dioxide, compared to the more typical mix of water and carbon monoxide found in solar system comets, may reflect this difference in elemental availability. Furthermore, the detection of carbon monoxide, water ice, and carbonyl sulfide in the comet's Coma suggests that its formation environment was not entirely devoid of heavy elements, but that the proportions of these elements differ from those in the solar system. The age and origin of 3I Atlas are not just academic curiosities. They are windows into the history of the Milky Way and the processes that shape planetary systems. By studying the comet's composition and trajectory, astronomers gain insights into the conditions that existed in its parent star system and the galactic environment in which it formed. These insights, in turn, inform our understanding of the diversity of planetary systems across the galaxy and the factors that influence their evolution. As 3I Atlas continues its journey through the solar system, it serves as a cosmic artifact, a relic of an ancient star system that has traversed the void to deliver its story to us. As 3I Atlas prepares to depart the solar system, its legacy extends beyond the data it provides. It is a beacon of possibility, a reminder that the universe is vast, interconnected, and teeming with mysteries waiting to be unraveled. The comet's journey has already sparked discussions about the feasibility of future missions to interstellar objects before they vanish into the void. Concepts like ESA's Comet Interceptor and NASA's proposed Dragonfly mission represent the next frontier in space exploration, aiming to study these rare visitors in unprecedented detail. Such missions would require meticulous planning and advanced propulsion technologies, but the rewards would be immense. By capturing samples from an interstellar comet, scientists could gain direct insights into the chemical and physical conditions of distant planetary systems, bridging the gap between the solar system and the wider galaxy. The challenges of reaching 3I Atlas highlight the logistical hurdles of interstellar exploration. Launching a probe from Earth to intercept the comet after its discovery in July 2025 would demand a delta V change in velocity of at least 24 kilometers per second, a feat beyond the capabilities of current propulsion systems. However, if such a mission were planned in advance, launching from Mars could reduce the required delta V to around 5 kilometers per second, making the endeavor more feasible. Mars-orbiting spacecraft, such as the Juno probe or the upcoming Jupiter Icy Moons Explorer JWST, may offer opportunities to observe 3I Atlas during its close encounter with the red planet in October 2025. While redirecting these spacecraft to study the comet could introduce risks to their primary missions, the potential scientific payoff is undeniable. Beyond the realm of practical missions, 3I Atlas has ignited debates about its nature. In July 2025, astrophysicist Avi Loeb speculated that the comet could be an extraterrestrial spacecraft, citing its anomalous characteristics, including its large size, lack of identifiable chemicals, and trajectory aligned with the solar system's ecliptic plane. While Loeb's hypothesis has been met with skepticism by the broader scientific community, it has prompted valuable discussions about the criteria for identifying artificial objects in space. Critics argue that the comet's cometary activity, as evidenced by its outgassing of carbon dioxide, water, and cyanide, strongly supports its natural origin. Additionally, the absence of detectable metals like iron, which are commonly found alongside nickel in cometary outgassing, further reinforces the case for a natural explanation. The debate surrounding 3I Atlas reflects the delicate balance between scientific rigor and open-minded inquiry. While extraordinary claims require extraordinary evidence, the mere possibility of encountering an artificial object from another civilization underscores the importance of maintaining a curious and critical perspective. As technology advances, future missions may provide the tools necessary to test such hypotheses definitively. Instruments capable of detecting non-natural structures or anomalies in the comet's composition could shed light on its true nature, whether it proves to be a natural interstellar traveler or something far more extraordinary. Ultimately, 3I Atlas represents more than just a scientific curiosity. It is a symbol of our place in the cosmos. Its arrival reminds us that we are not isolated in the universe, but part of a vast web of celestial bodies and processes that transcend the boundaries of individual star systems. As it continues its journey beyond the solar system, 3I Atlas leaves behind a trail of questions that will drive future exploration and discovery. What other interstellar visitors await us? What secrets lie hidden in the chemistry of comets from distant systems? And what will we learn about the origins of life and the structure of the galaxy as we unravel the mysteries of these cosmic messengers? The answers to these questions may lie in the next interstellar object to grace our skies. Until then, 3I Atlas serves as a testament to the power of curiosity and the enduring human desire to seek out the unknown. In the vast, uncharted expanse of the cosmos, where stars burn like distant lanterns and galaxies swirl in silent symphony, the arrival of 3I Atlas stands as a profound reminder of the universe's boundless interconnectedness. Discovered on 1 July 2025 by the Atlas Survey Telescope in Chile, this interstellar comet is not merely a transient visitor to our solar system. It is a relic of another stellar neighborhood, a traveler born in the cradle of a distant star's planetary dance. With its hyperbolic trajectory and blistering speed of 58 kilometers per second, 3I Atlas defies the gravitational embrace of the Sun, hurtling through the inner solar system like a ghostly specter from the depths of interstellar space. Its path, marked by the precision of celestial mechanics and the randomness of cosmic chance, invites us to ponder our place in a galactic tapestry woven with the threads of countless other worlds. What makes 3I Atlas particularly remarkable is its status as the third confirmed interstellar object to cross our cosmic doorstep, following in the footsteps of 1I Oumuamua and 2I Borisov. Yet, unlike its predecessors, 3I Atlas carries with it a unique signature of its origins. Observations by the Hubble Space Telescope and the James Webb Space Telescope have revealed a nucleus cloaked in a coma of carbon dioxide-rich gas, a composition starkly different from the icy mixtures of solar system comets. This anomaly hints at a formation history unlike anything we've encountered before, a story etched in the chemistry of its volatile ices and the traces of nickel and cyanide detected in its wake. As it glides through the inner solar system, 3I Atlas is not just a scientific curiosity, it is a cosmic envoy, bearing messages from a star system we may never see, yet whose influence reaches across the void. The arrival of 3I Atlas compels us to confront a humbling truth. Our solar system is not an island in the cosmos. It is part of a vast dynamic network of stars, planets, and interstellar wanderers, each contributing to the ongoing exchange of matter and energy that shapes the fabric of the galaxy. In its brief passage, 3I Atlas serves as a bridge between the familiar and the unknown, a fleeting touchstone in humanity's quest to understand the universe's deepest mysteries. As we turn our gaze to this interstellar traveler, we are reminded that the cosmos is not a silent, indifferent void, but a living, breathing entity, one that whispers its secrets in the language of light and motion. To comprehend the significance of Three-Eye Atlas, one must first unravel the intricate dance of celestial mechanics that governs its trajectory. Unlike the elliptical orbits of planets and native comets, which are bound to the sun's gravitational pull, Three-Eye Atlas follows a hyperbolic path, a trajectory so energetic that it will escape the solar system entirely. This distinction is not arbitrary. It is a testament to the comet's birthplace in the gravitational realm of another star. The sun's gravity, though immense, cannot ensnare an object moving at a hyperbolic excess velocity of 58 kilometers per second, a speed that far surpasses the 26 kilometers per second and 32 kilometers per second velocities of 1I Oumuamua and 2I Borisov, respectively. This velocity, combined with its orbital eccentricity of 6.1414, paints a picture of a comet that is not merely passing through but racing away, destined to vanish into the interstellar abyss. The mathematics of Three-Eye Atlas's journey reveals a tale of cosmic chaos and order. Its trajectory, defined by the interplay of gravitational forces and the comet's innate momentum, is a product of its origin in the Milky Way's disk. Astronomers have traced its path to the direction of the constellation Sagittarius, near the galactic center, a region teeming with ancient stars and nebula remnants. Here, Three-Eye Atlas likely formed within the protoplanetary disk of a long-vanished star, its icy nucleus sculpted by the cold, dark expanse of interstellar space. Over billions of years, gravitational interactions with neighboring stars or planets may have catapulted it into the galactic void, setting it on a collision course with the solar system. The comet's journey is further complicated by the vertical component of its velocity relative to the galactic plane. With a Watts component of 18.5 kilometers per second, Three-Eye Atlas is ascending through the Milky Way's disk, a motion that suggests it belongs to either the thin or thick disk population of stars. The latter, composed of older stars with lower metallicity, offers a tantalizing clue to the comet's age. Studies estimate that Three-Eye Atlas could be between 7.6 and 14 billion years old, far older than the 4.6 billion-year-old solar system. This staggering antiquity raises profound questions. What processes shaped a world so ancient? And what secrets does its composition hold about the early days of the galaxy? As Three-Eye Atlas approaches its perihelion on 29 October 2025, its interaction with the Sun will provide critical insights into its nature. The Sun's heat will sublimate the comet's volatile ices, triggering the release of carbon dioxide, water vapor, and other gases that form its coma. These emissions, observed by telescopes like Hubble and JWST, offer a glimpse into the comet's internal structure and the conditions of its distant birthplace. The detection of nickel and cyanide in its coma adds another layer of complexity, hinting at chemical processes that may differ from those in the solar system. Each observation is a piece of a puzzle, a fragment of knowledge that brings us closer to understanding the origins of this interstellar traveler, and perhaps by extension, our own cosmic lineage. The existence of Three-Eye Atlas and interstellar objects like it challenges our anthropocentric view of the universe. For centuries, humanity has gazed at the stars and imagined them as distant, indifferent lights, celestial bodies that exist in isolation from our own. Yet Three-Eye Atlas shatters this illusion, revealing a cosmos where matter, energy, and even life's building blocks are exchanged between stars. This interstellar exchange, often referred to as panspermia, posits that organic molecules, or even microbial life, could hitch rides on comets and asteroids, spreading the seeds of biology across the galaxy. If Three-Eye Atlas carries such materials, it becomes not just a visitor, but a courier of cosmic heritage, a vessel ferrying the raw ingredients of life from one star system to another. This concept redefines our understanding of the solar system's place in the universe. No longer a self-contained oasis, it emerges as a node in a vast, interconnected web of stellar ecosystems. The Milky Way, with its hundreds of billions of stars, is not a static backdrop but a dynamic arena where planetary systems collide, merge, and exchange material. Comets like 3I Atlas are the messengers of this cosmic dialogue, their trajectories mapping the invisible currents of gravitational tides that bind the galaxy together. In this context, the arrival of 3I Atlas is not an anomaly, but a natural consequence of the Milky Way's evolutionary dance. A reminder that the universe is not a collection of isolated worlds, but a living, breathing entity. Moreover, 3I Atlas forces us to confront the limits of our knowledge. Despite decades of technological advancement, we remain spectators to the grandeur of the cosmos, capable of observing, but not yet of touching the objects that traverse our skies. The comet's hyperbolic escape velocity renders it inaccessible to current spacecraft, a sobering reminder of the vast distances and energies that define the universe. Yet even in its inaccessibility, 3I Atlas inspires awe. Its journey, spanning billions of years and light years, is a testament to the resilience of matter and the enduring power of motion. As it departs the solar system, leaving behind a trail of gas and dust, it carries with it the quiet promise of future discoveries of other interstellar travelers, of new worlds waiting to be found, and of the infinite possibilities that lie beyond our cosmic horizon. Amid the scientific consensus that 3I Atlas is a natural comet, a provocative hypothesis emerged in July 2025, challenging the boundaries of our understanding. Astrophysicist Avi Loeb and colleagues from the Initiative for Interstellar Studies speculated in a paper published on Archaeology that 3I Atlas could be an extraterrestrial spacecraft, citing its anomalous trajectory, apparent size, and lack of detectable chemicals as potential indicators of artificial origin. This claim ignited a firestorm of debate within the astronomical community, with many researchers criticizing Loeb's assertion as speculative and lacking empirical support. Critics argued that the comet's observed cometary activity, confirmed by Hubble, JWST, and the Swift Observatory, clearly demonstrated its natural character, while the absence of certain chemicals could simply be attributed to its distance from the Sun and the limitations of current observational techniques. Yet the controversy surrounding Loeb's hypothesis underscores a deeper tension in modern astronomy: the balance between open-minded curiosity and the rigor of scientific methodology. While extraordinary claims demand extraordinary evidence, the mere act of questioning the natural origins of interstellar objects reflects humanity's enduring fascination with the possibility of extraterrestrial intelligence. Loeb himself acknowledged that 3I Atlas is almost certainly a comet, framing his speculation as a thought experiment designed to stimulate discussion rather than a definitive conclusion. Still, the debate highlights the fragility of our assumptions about the cosmos. If interstellar objects like 3I Atlas can challenge our understanding of planetary formation, what other surprises await us in the uncharted realms of the galaxy? This episode also reveals the cultural and philosophical dimensions of scientific inquiry. The idea that 3I Atlas might be an alien artifact resonates with our collective imagination, tapping into ancient myths of cosmic visitors and modern anxieties about humanity's place in the universe. Whether or not the comet is a spacecraft, its journey reminds us that the cosmos is vast, mysterious, and full of stories yet to be told. As 3I Atlas departs the solar system, it leaves behind not just a trail of gas and dust, but a lingering question: are we truly alone in the galaxy? Or are we too the children of interstellar wanderers? As 3I Atlas vanishes into the depths of interstellar space, it leaves behind a legacy that transcends its physical presence. The comet's journey has not only expanded our scientific knowledge, but also deepened our appreciation for the interconnectedness of the cosmos. Its carbon dioxide-rich coma, nickel-laced emissions, and ancient origins serve as a cosmic Rosetta Stone, offering clues about the conditions that shape distant star systems and the processes that govern the exchange of matter across the galaxy. Yet beyond these tangible discoveries lies an intangible truth. The universe is a story of motion, transformation, and continuity. Every atom in our bodies, every star in the night sky, and every interstellar traveler like 3I Atlas is a thread in this vast unfolding narrative. The study of 3I Atlas also underscores the importance of international collaboration in modern astronomy. From the Atlas survey in Chile to to the Hubble Space Telescope's vantage point above Earth, the comet's discovery and characterization have been made possible by the shared efforts of astronomers, engineers, and institutions across the globe. This cooperative spirit mirrors the very essence of the cosmos itself, a system where stars, planets, and interstellar objects do not exist in isolation, but interact in complex symbiotic relationships. As 3I Atlas departs, it carries with it the hope that future discoveries will continue to bridge the gaps between disciplines, cultures, and generations, uniting humanity in our quest to understand the universe. Yet the departure of 3I Atlas is not the end of its story. In the years to come, its trajectory will be retraced, its composition analyzed in greater detail, and its origins debated anew. The data it left behind will fuel the imaginations of scientists and dreamers alike, inspiring new technologies, new theories, and perhaps even new questions that we have yet to ask. And as we stand beneath the stars, watching the comet fade into the void, we are reminded that the universe is not a static monument to the past, but a living, evolving entity, one that continues to surprise, challenge, and inspire us with its infinite complexity. In the end, 3I Atlas is more than a comet. It is a symbol of our relentless curiosity, a testament to the power of science to illuminate the unknown, and a reminder that the cosmos is not a distant, indifferent realm, but a home we share with countless other worlds. As its light dims in the sky, we are left with a simple yet profound realization. The universe is vast, yes, but so too is our capacity to explore it. In the vast, star-strewn expanse of the Milky Way, a silent traveler glides through the void, a comet born long before Earth itself. 3I Atlas, the third interstellar object confirmed to have traversed our solar system, is more than a fleeting visitor. It is a messenger from a forgotten epoch, carrying secrets of a galaxy older than the stars we see today. Discovered in July 2025 by the Atlas telescope in Chile, this enigmatic wanderer emerged from the depths of interstellar space, its path etched by the gravitational tides of a universe teeming with motion and mystery. As 3I Atlas hurtles inward at a blistering 58 kilometers per second, it defies the gentle embrace of the sun's gravity, destined to escape the solar system as swiftly as it arrived. Unlike the countless comets that originate in our own backyard, the Oort cloud or the Kuiper belt, this interloper hails from another star system, a relic of a cosmic nursery now lost to time. Its hyperbolic trajectory, a signature of interstellar birth, marks it as a rare and precious artifact. Yet its true marvel lies not in its speed or its origin, but in its age. Estimates suggest 3I Atlas is between 7 and 14 billion years old, predating our solar system by billions of years. To witness this comet is to glimpse a fragment of a primordial universe, a world that once danced among stars now long extinguished. What makes 3I Atlas even more extraordinary is its composition. Unlike the icy wanderers of our own solar system, which carry traces of water and carbon-based molecules, 3I Atlas is a treasure trove of carbon dioxide, a substance that hints at its formation in the frigid outskirts of a distant protoplanetary disk. Its Coma, a swirling cloud of gas and dust, glows with the spectral signatures of cyanide and nickel, elements that echo the raw materials of life itself. Every observation of this comet adds a brushstroke to the cosmic canvas, revealing a story written in ice and chemistry. And yet, for all its scientific richness, 3I Atlas remains a fleeting presence. By late 2026, it will vanish into the abyss, leaving behind only questions and a profound reminder of the universe's boundless, untold histories. To comprehend 3I Atlas is to unravel the intricate physics of its journey. At the heart of its identity lies its hyperbolic trajectory, a path so steeply angled and swift that it cannot be captured by the sun's gravity. This is a comet not bound to the solar system but merely passing through, a transient guest in a cosmic theater. Its hyperbolic excess velocity of 58 kilometers per second, 36 min/sis, is staggering, far exceeding the speeds of its interstellar predecessors, 1I Oumuamua, 26 kilometers per second, and 2I Borisov, 32 kilometers per second. Such velocity implies that 3I Atlas has traveled vast distances across the galaxy. Propelled by forces we can only begin to imagine, the comet's orbital eccentricity of 6.141, a measure of how sharply its path curves, is a testament to its freedom. Most objects in the solar system follow elliptical orbits, looping around the sun in predictable rhythms. 3I Atlas, however, follows a trajectory so elongated that it appears almost straight line in the grand scale of space. This extreme eccentricity places it among the most dynamically distinct objects ever observed, a needle threading through the fabric of the galaxy. Its closest approach to the Sun, 1.36 astronomical units, AU, will occur on 29 October 2025, placing it between the orbits of Earth and Mars, though it will never threaten our planet. Its proximity allows telescopes to peer into its heart, dissecting its secrets with unprecedented clarity. Yet what truly sets 3I Atlas apart is its origin. Tracing its path backward through the stars reveals that it entered the solar system from the direction of the Milky Way's thick disk, a region populated by ancient stars with compositions unlike our own sun. The thick disk, a relic of the galaxy's violent youth, is a graveyard of stars and debris, a place where time stretches back to the dawn of the cosmos. Here, 3I Atlas likely formed in the icy periphery of a dead star system, its nucleus sculpted by the slow erosion of time and stellar winds. The comet's high vertical velocity, 18.5 kilometers per second relative to the galactic plane, suggests it belongs to this population, a wandering remnant of an era when stars were closer and collisions more frequent. The dynamics of 3I Atlas's journey are not merely academic. They offer a window into the chaotic, interconnected nature of the galaxy. Interstellar comets like 3I Atlas are born in the gravitational crucibles of young star systems, ejected by the gravitational slingshots of giant planets or passing stars. Once adrift, they drift for eons, their paths dictated by the unseen hands of galactic currents. Some may collide with stars, others may be captured by distant worlds, but most, like 3I Atlas, continue their lonely voyages, silent witnesses to the universe's ceaseless evolution. The scientific scrutiny of 3I Atlas has yielded revelations that defy expectation. Its nucleus, shrouded in a coma of gas and dust, remains elusive in size. Estimates place it between 0.32 and 5.6 kilometers wide, though the most likely figure is under a kilometer. This ambiguity stems from the comet's prodigious outgassing, a phenomenon driven by the sun's relentless heat. As 3I Atlas draws closer to the sun, its icy core begins to sublimate, releasing carbon dioxide, water vapor, and other volatiles in a process akin to a slow, silent explosion. The resulting coma, stretching millions of kilometers in all directions, transforms the comet into a glowing specter, its dust and gas trailing like a ghostly veil. What captivates scientists most, however, is the comet's chemical fingerprint. The James Webb Space Telescope, JWST, has detected an extraordinary abundance of carbon dioxide in its coma, 8 times the ratio of carbon dioxide to water seen in typical solar system comet. This anomaly suggests that 3I Atlas formed in a region far colder than the Kuiper Belt, perhaps beyond the CO₂ frost line of its parent star's protoplanetary disk. The presence of water ice, though faint, hints at a complex history of preservation and exposure. Meanwhile, the Very Large Telescope, VLT, has uncovered traces of cyanide and atomic nickel vapor, elements that mirror the volatile chemistry of solar system comets, yet hint at exotic processes at play. The comet's activity itself is a paradox. Despite its distance from the Sun, initially 4.5 AU when discovered, 3I Atlas was already active, emitting dust and gas as early as May 2025. This premature activity, observed by NASA's TESS satellite, challenges models of cometary behavior, suggesting that 3I Atlas may harbor a reservoir of highly volatile ices, such as carbon monoxide, that sublimate at greater distances than water. The Hubble Space Telescope's sharp-eyed observations have further revealed a nucleus that, despite its small size, ejects dust at a rate comparable to 2I Borisov. These findings underscore the comet's uniqueness, It is neither a typical solar system comet nor a mere interstellar oddity, but a bridge between two cosmic realms. Perhaps most haunting is the possibility that 3I Atlas is older than the solar system itself. If it indeed hails from the thick disk of the Milky Way, it could be 7 billion years old, a relic of a time when the galaxy was young, its stars forming in frenzied bursts of creation. Such an age would make 3I Atlas a survivor of epochs we can scarcely fathom, a wanderer that has witnessed the births and deaths of stars now long vanished. Its journey through the galaxy may have been punctuated by close encounters with other stars, each one altering its trajectory and composition. Yet despite these trials, it persists, a fragile yet enduring symbol of the universe's resilience. As 3I Atlas prepares to depart the solar system, its legacy is already etched into the annals of astronomy. The data gathered by Hubble, JWST, and ground-based observatories will keep scientists busy for decades, unraveling the threads of its history and the broader tapestry of interstellar comets. Yet, for all its scientific value, 3I Atlas also serves as a humbling reminder of our place in the cosmos. We are but fleeting observers of a universe that has existed for 13.8 billion years, a cosmos where time and space stretch beyond comprehension. The comet's journey mirrors our own, temporary, yet meaningful. Just as 3I Atlas carries the echoes of a distant past, so too do we carry the memory of stardust within us, forged in the hearts of ancient stars. Its passage through the solar system is not merely an event but a metaphor, a reminder that we are part of a grand, interconnected story, one that transcends the boundaries of time and space. In the coming months, as 3I Atlas fades into the darkness, we will turn our gaze to new horizons. The Vera C. Rubin Observatory, with its unprecedented sensitivity, may yet uncover more interstellar visitors, each one a puzzle waiting to be solved. And perhaps, in studying these cosmic wanderers, we will come closer to understanding not only the universe, but ourselves. For in the quiet glow of a comet's coma, in the silent flight of an interstellar traveler, we find a reflection of the infinite, a journey that began long before us and will continue long after we are gone.